Hello, Dr. Somo.
Yes.
Yeah, I think only first speaker I will introduce, na?
First and second.
Second.
Yeah, first and second, and after that, after break, we will. Yeah. So let's just wait 5 more minutes, maybe.
Okay.
And other people can join also.
Yeah, we have time.
Yes, we do.
Now, what I'm telling, you can introduce the second speaker.
Just a second. I'm calling you. Just a second. Good afternoon and good morning and good evening, wherever you are. I think we should wait a couple of more minutes. Takahiro, hello. Let's just wait a couple of more minutes because I know some people are trying to join and they haven't been able to join so far. So I suggest we join just 2-3 more minutes and then we start. Okay. Ranjita, also just in a few minutes we will start. Just 2-3 minutes.
Yeah. At 2-3 we can start.
Okay.
Yeah. Hello, Somo. Hello, Dr. Somo.
Yes.
Yeah, I think we can start.
So good afternoon, everyone, and good morning, good evening, and welcome to the fourth and final day of this meeting, Fracmeet 2021. And can I ask Professor Ranjit Thapa, who is the head of the Department of Physics in SRMAP, to please chair the session. So Ranjita, over to you.
Yeah, thank you, Dr. Somo. So I wish to invite Professor Takahiro Hatano from Osaka University, Japan, to deliver the invited talk. The title of the talk is Models for Slow Earthquake. So it is over to you, Professor Hatano.
Thank you. So I'd like to share the screen.
Yeah, so Somo, can you off your screen sharing, Dr. Somo?
Okay.
Yeah, now we can share. Takahiro.
Yeah, it seems like I can share the screen. No. Can you see the slides? Maybe no.
We can see the slides. It's not in full screen, but we can see it.
Okay.
Now it's gone.
Okay, and oops. about this?
We see the screen, but your entire desktop.
Okay, then.
Yeah, now it's ready.
Okay.
Yes.
Okay, so thank you very much for the invitation. I would like to thank the organizers for this wonderful invitation to this Fracmeet. And unfortunately for this time, I cannot meet my dearest Indian friends. Hopefully the next year, I'm looking forward to seeing you guys in India. So my talk will be about earthquakes, especially slow earthquakes, which you guys might not be so familiar. So I'm gonna talk about more instructive part about earthquakes, including what slow earthquakes really are. So this work is done in collaboration with Kota Fukuda, who was my PhD student in the University of Tokyo, and also master course student, Yuta Nagano in Osaka. So these very impressive photos are taken from the internet, and all of them were taken during the Kobe earthquakes in 1995. So this earthquake was magnitude 7, but because the earthquake fault was very close to the downtown Kobe, so the damage was very bad. And what causes the seismic waves, which causes serious damage to the infrastructure? And this was caused by the sudden motion or sudden slippage of earthquake force, which sometimes you can see on the surface of the Earth. So these photos are also taken at the Kobe earthquakes in 1995, where you can see a very sharp slip interface of the earthquake force. And actually, you can see this very sharp slip interface in a museum called Nojima Fort Museum, which is located not very far from Kobe City, or you can go here even from Osaka after 1.5 hour drive. So this conference, many people talk about rupture or fracture dynamics. And earthquake is also a kind of rupture process, but it involves much larger scale, sometimes hundreds of kilometers. So it sometimes have common aspects with the rupture in material science, because of the scale dependence or the scale difference. Sometimes we can encounter a very different nature than those in laboratory scale, and that makes the science of earthquakes more difficult, but at the same time it can be more interesting from the scientific point of view. So from a seismological point of view, we can actually infer how earthquake faults slip during earthquakes. So this is results obtained by seismic inversion taken at the magnitude 9 Tohoku earthquakes, which occurred 10 years ago. Coincidentally, this is 10 years ago today. It was March 11th. So here you can see the rupture initiated, of course, the Sendai city located here. And rupture propagated asymmetry on the fault plane. And this is 10 seconds after the rupture initiation, and this is 40 seconds after the rupture initiation. And the rupture extends on the fault plane for more than 2 minutes. So it was a very huge rupture. And I said this was the magnitude 9 gigantic earthquakes. So the size of the earthquakes is characterized by the quantity called magnitude. And this magnitude is actually not unique. So there are various definitions on magnitude, but the most physical definition is called the moment magnitude, which you can see on this slide. And this moment magnitude is defined through a quantity called seismic moment. And here, the seismic moment is denoted by MO. And here, G is the shear modulus of rocks, and it is a constant. And here, D is the relative displacement on the fault plane. Suppose this XY are the coordinates on the fault plane. So the relative displacement is a function of X and Y. So, and we gonna integrate this D with respect to the entire fault, and multiplied by the shear modulus, we can compute this seismic moment. And by using this seismic moment, we can end up with the moment magnitude by taking the common logarithm of the seismic moment. And here we have some constant, but this constant is chosen so that the definition of moment magnitude is compatible with those previously defined in a seismic manner. So this is the magnitude. And probably the most famous statistical law about earthquake would be the Gutenberg-Richter's law. And in short, this law states that larger earthquakes are less frequent. So we have numerous smaller earthquakes. And in terms of the cumulative distribution function, the probability or the number of earthquakes having magnitude larger than m is written like this in an exponential manner. Here we have a constant b, which is typically ranging from 0.7 to 1.4. So because this magnitude here is defined in terms of the log of the seismic moment, so this exponential law is reduced to the power law with respect to the seismic moment. So this states that the probability distribution function for seismic moment is power law. So the size of the earthquake, which is characterized by the seismic moment, is scale-free. And this is just one example taken from the Japanese earthquake catalogs called the JMA catalog, and taken from a certain area called Iwate Prefecture for a certain period. So you can see this Gutenberg-Richter law holds well. And this is just one example, but this Gutenberg-Richter law holds the almost everywhere in the world. So in that sense, it is very reproducible and very universal law about earthquakes. And the other important aspects on the earthquakes are the correlation in the time domain. So in short, we can say that many earthquakes can follow earthquakes. In here, we have an earthquake catalog taken from Southern California. And this is actually a famous earthquake called Landers earthquakes. So we have two major earthquakes here and here. And before this first one, we have less number of earthquakes. But after this large one, many aftershocks follow. And here we have even larger one, new main shock, and then many aftershocks follow. So obviously, with this, we can see that earthquakes occurrence is a non-Poissonian process. So there exists a very strong correlation in the time domain. So the waiting time distribution is an important quantity to characterize such a non-Poissonian process about earthquake occurrence. And the functional form of the waiting time distribution of earthquakes depends on the region and also the time, the time period, whether it would be a quiescent period or a very aftershock period. But it is well known that if we focus on the quiescent or the steady state, it is described by the gamma distribution with a very small exponent, something like 0.2 or 0.3. So what I have explained about regular earthquakes. So, but what are the slow earthquakes? So in short, they are earthquakes that does not emit seismic waves. And nowadays, there have been known many kinds of slow earthquakes. But the first one was discovered almost 20 years ago by Professor Obara. And it was called non-volcanic tremors, which looks very similar to very weak earthquakes that occur in volcanoes. But because there are not volcanoes where he found these non-volcanic tremors, it was actually the subduction zone. So he named that as non-volcanic tremors. And it emits very weak seismic signals that contains a very lower frequency seismic waves. So after that, nowadays we know many kinds of slow earthquakes, and that they make a very apparent contrast between regular earthquakes. So some might be interested in the dynamical instability in understanding earthquakes. So usually regular earthquakes are regarded as stick slip instability, like in bottom movies like this. But in upper part, the motion is more steady. But there is a continuous spectrum with respect to the steady motion and the non-steady motion or unstable motion. So somewhere in between, we may have some intermediate stability, and that may correspond to slow earthquakes. Actually, in subduction zone, we may interpret such instability depending on how deep the seismic region locates. Usually, we know that in very shallow part or very deep part, we don't have earthquakes at all. So in deeper part or in deeper very shallow part, the motion would be like this, very steady motion, and there are no earthquakes. But in intermediate region, we have gigantic earthquakes sometimes. So this blue area is called the seismogenic zone. And in between the steady zone and the seismic zone, we have some intermediate zone where we can observe many slow earthquakes. And with this, we usually infer that the temperature is high in a very deeper part, so the sleep is stable. But this in intermediate region, we have very marginal instability, so we have a very strange kind of earthquakes. So there are continuous spectrum about earthquakes. The fastest slow earthquakes are called low frequency earthquakes or tectonic tremors. And they emit very weak seismic signals. And slightly slower than these low frequency earthquakes or tectonic tremors. There are very low frequency earthquakes or deep low frequency earthquakes, which have intermediate magnitude ranging from 3 to 4. And these smaller but faster events have magnitude of 0 to 1 or 2. And we have slower events called slow slip events. And these slow slip events do not emit any seismic waves, so we cannot detect these slow slip events by seismometers. So these events can be detected only by the geodetic measurement like GGBS. So here we have seismic signals, and here we don't have seismic signals. And what we're gonna focus here as a physical modeling is these members that emits very weak seismic signals. And what is very remarkable with respect to slow earthquakes are the scaling behavior. So here the scaling variation involves the seismic moment that I have explained, and also the duration of slow earthquake. So if the duration is longer, then generally the seismic moment is also large. And that is also true for regular earthquakes. But for regular earthquakes, the seismic moment is proportional to the cube of the duration. Whereas for slow earthquakes, we have this scaling relation. The seismic moment is just proportional to the duration of the event. So there are qualitative difference between regular earthquakes and slow earthquakes. And the second remarkable difference between regular and slow earthquakes is the power spectrum of the moment rate. Here, the moment rate is defined by the time-dependent seismic moment. Here, the seismic moment depends on time through the displacement field on the fault. So during an earthquake, we can observe the relative displacement on the fault as a function of the position and the time. And that makes the seismic moment time dependent. So we can see the power spectrum of this quantity. And this quantity is calculated from the seismic signals. And it is well known that power spectrum of seismic moment is proportional to the omega to the minus fourth for regular earthquakes. But slow earthquakes have much richer low frequency components on their seismic signals. And it is just proportional to the omega to the minus squared. So this is again the qualitative difference between regular and slow earthquakes. So we're gonna propose a model that can somehow reproduce these properties. The first one is the moment duration scaling, which is different from regular earthquakes, and also the power spectrum of the moment, the seismic moment rate. And also the GR law holds for the tectonic tremors. But it is still somewhat controversy as to whether if the GR law holds for slow earthquakes. But now we're gonna have certain evidence that the GR law also holds for slow earthquakes. So the GR law can be also our target by considering the model for slow earthquakes. In gradients, we gonna focus in modeling through earthquakes is competing timescales. Usually, we have two timescales regarding earthquakes or any rupture phenomena. So the first one is a stress release rate, which may be deeply involved with rupture propagation velocity and material failure or earthquake process. The second one is the loading rate. So usually this loading rate is much smaller than the stress release rate because the rupture is dynamically unstable phenomena. So usually the process is very fast. So the former is much larger than the latter. And this is true for regular earthquakes, but this is not necessarily true for slow earthquakes. And actually, these two timescales are more or less comparable in slow earthquakes. So in case of regular earthquakes, this timescale are different by 9 orders of magnitude. But for slow earthquakes, it can be as small as 10 to the minus third or 10 to the minus fourth, or even just 10 times larger for the case of slow sleep events. So for the slow earthquakes, actually we can see that these two timescales are competing. So we're gonna incorporate the effect of these two competing timescales in a very simple model for earthquakes. This is actually well known in the field of statistical physics of earthquakes. And this is called OFC model, taken after Orami, Feather, and Christensen. And this is a variation of the self-organized criticality model, where we have two-dimensional square lattice. And on each cell, the continuous internal variables are defined. And this variable ranges from 0 to 1. And as usual, the loading is done on each cell uniformly and in a constant rate. But here we have a time step. And in each time step, the cells are loaded with R times dt. And in each time we scan the entire cell, and if this internal variable exceeds the threshold, which in this case is set to 1. So if S is larger than 1, then it topples and redistribute its own internal variable to the 4 nearest neighbors. But it involves some dissipation. So usually this guy redistributes the internal variable to 4 nearest neighbors with alpha. But this alpha is usually set to be smaller than a quarter. And here, because we have a dynamics, in one time step, one cell, sorry, in each time step, each cell can topple only once. So in other words, in one time step, we have loading process and toppling process and redistribution process. This is done in one time step, and this procedure is repeated in each time step. So it's a kind of OFC model, but because we have a time scale, so we may name it as a dynamic OFC model. And here the R, the parameter R plays a central role, which is defined by the ratio of the two rates, which are the loading rate divided by the stress release rate. In conventional OFC model, where we have a very slow loading rate, so in conventional model, R equals 0, but here we consider the finite non-dimensional loading rate. So because we have two-dimensional system, we can easily visualize the system like this, and the dynamics of the system looks like this. Here, each cell has an internal variable, and the size of these circles represents how large the internal variables. So it somehow look like soda or any forms in soda. So here we have R equals 10 to the minus third. So it's a bit faster loading rate. So faster loading. And this is for the 10 to the minus fifth loading rate. So it's a bit smaller, bit slower. And looks like very similar. So we're gonna observe a time series of the stress release rate or the internal variable, how the internal variable is released as a function of time. Here the horizontal axis is a time step, and the vertical axis is the moment rate, which is defined by the released internal variables at each time step. So here we have a sequence of the stress release event. So if the event starts here, and we have non-zero moment rate, and right after this moment rate goes to 0, we interpret this moment as the end of the seismic event. So this defines a single event, and same goes here. And if we have a larger loading rate, the one event can hardly stop like this. So we have a series of stress release events. So this is the mean event duration as a function of non-dimensional loading rate. And here, if the loading rate is small, the mean duration is almost independent of the loading rate, but it is actually goes very larger if it exceeds characteristic loading rate, R sub C. And this means that the mean duration increases with the non-dimensional loading rate in an exponential manner. And this characteristic loading rate depends on the system size, actually, and this is inversely proportional to the system size. And this is the event size distribution in our dynamic OFC model. And it is well known that in conventional OFC model, the GR law holds, and so is in our model. But in here, the B value for the Gutenberg-Richter law is also dependent on the loading rate R. And if we have a larger loading rate, then the B value decreases. And this is the power spectrum of the moment rate. And we can see a very nice fit to the Lorentzian spectrum like this. So with this, we can define the correlation time by using the corner frequency of the Lorentzian spectrum. And this is how the correlation time behaves as a function of the time that the simulation starts. So if this correlation time depends on the time, then we are still in transient. And after a certain time, we reach steady state. So we can use only the statistics after the system reaches a steady state. And actually, this correlation time at steady state also depends on the system size. But in this case, it is very non-trivial dependence. So this is a non-integer exponent ranging from 0.4 to 0.6. But this exponent also depends on the dissipation parameter alpha. And power spectrum is Lorentzian, and it looks like almost independent of the loading rate. But if the loading rate is larger than RC, which is a critical value at which the events never stop. So in here, if R is larger than R sub C, then we still have a slope which is proportional to omega minus squared. But now we don't have a lower frequency part. But here, the corner frequency is independent of the loading rate. So this time scale in the system is rather independent or insensitive to the loading rate. And this is the event declaration as a function of the seismic moment, mean seismic moment as a function of the mean duration. So in here, we have smaller events, and in here, we have larger events. And this scaling narration somewhat differs depending on the size of the event. And for smaller events, it has some non-trivial behavior with respect to the duration. And this beta ranges from 1.5 to 1.9, depending on alpha. But for large events, in here, this scaling exponent is independent of the dissipation parameter alpha. And because this slope is 1, here beta is 1, so we retain the linear scaling relation between the seismic moment and the duration, which resembles the observations on slow earthquakes. So this is the waiting time distribution in our model. So the waiting time distribution is taken from this kind of time series. Here we can define the quiescent period at which we don't have any toppled sites, and can take the waiting time distribution for the 2 consecutive seismic events. And for our model, we have Weibull distribution instead of gamma distribution, which is usually obtained for regular earthquakes. And here the exponent P is almost 1, but it's more or less 0.9. So it's a bit different from the Poissonian process, but more or less almost indistinguishable from the Poissonian process. So this concludes my talk. So here we propose the dynamic OFC model where we can incorporate the competing 2 time scales, which are the loading rate and the stress release rate. And similar to conventional OFC model, we found that the GR law holds and the B value decreases as a function of R, but it's a very small dependence. And analysis on moment rate shows that the power spectrum is Lorentzian, and it is consistent with the seismic observations on tectonic tremors. And here we have discrete cells, so we don't actually interpret the system size, but here the correlation time can be very interesting from the viewpoint of the real seismic waves. So we can further discuss what is this correlation time in observations. And we have more enduring events for larger loading rate. And here T denotes the mean duration. So if R exceeds R sub C, then we have very long events. And we also find the Weibull time distribution. The waiting time distribution is Weibull distribution, but so far we don't have any seismic observations about the waiting time distribution for slow earthquakes. So we need to talk to the seismologists about this. And that's it for my talk, and thank you very much for listening.
Yeah, thank you, Professor Hatano. Now the session is open for question and answer. If anyone have any question, please unmute or raise your hand to discuss with Professor Hatano. Anyone from audience?
Hi, Takahiro, thank you for this presentation. I was wondering, I mean, of course, in your OFC model, you can increase your, the stressing rate, capital R, easily. But in the Baryshnikov model, I mean, does one, I mean, if the pulling velocity is increased, will it kind of resemble your R, or can it take care of your R increase? And can one see there that with pulling velocity, the B value decreases there?
That's a good question. I should have checked that. Yeah, maybe yeah, some people checked how this pulling velocity in Baryshnikov model can affect the GR law. I have a bad memory, so now I don't remember. Yeah, but it surely affects the B value, or also in the Baryshnikov model. So yeah, it would be very interesting to compare the results between the model, I mean the dynamical C model and the Baryshnikov model.
Yeah. I mean, of course, R is very simple to manipulate in OFC model, but I don't know. But B, I mean, if it is clear that B value changes, decreases with increasing R, then that should happen perhaps also in the Baryshnikov model with increasing spooling velocity. But I have not seen such results. But anyway, I mean, okay. So if you see some results already published, you can kind of inform us.
No, thank you very much.
Okay.
I will show you.
Yeah.
Can I just add to that? Actually, when I was working with Hiro, we started on that particular thing, and we did see that with pulling velocity, indeed the GR law changes the exponent to a lower value. Unfortunately, I mean, mainly I did not write this out, but yeah, it happens. It quite clearly happens.
Oh, I see. I see.
Yeah. Yeah.
Is this Shomo? I mean, I didn't get who is this.
Yeah, it is me.
Yeah.
I'm the culprit here.
Yeah,
and
so
yes,
you didn't publish that finally.
Unfortunately, we didn't.
Okay, no, I think, I mean, now we should, because, I mean, these things are being shown there. And yeah, this should be compared then. Yeah.
Yes, definitely, yes. Jan has a question.
Yeah, so next question is by Iron Man.
Okay, well, first, thank you very much, Takahiro. That was a very interesting talk. So many observations kind of wrapped in to motivate the model, and some very nice agreement between the model and observation, and also an evocation to look more closely at the waiting times. The question really was, I mean, the major innovation here is putting in a finite duration to the local stress release. So I just wondered if, maybe you did say this, but I maybe missed it, but how does the stress transfer occur if you replace a step function with a ramp? Do you gradually increase the stress on the neighbors? Or what's the detail of how you actually do the stress transfer? Is it kind of a ramp function?
Stress transfer is actually done in a step function-like manner, in a single time step. So it is actually not a continuous function with respect to this. Yeah.
So what physically does the relaxation rate correspond to in the model? If there isn't a ramp, you know.
Okay. It is just a guess, but we wonder if this stress transfer system may be interpreted as the hydration or the diffusion of the interpore fluid, which may be activated by the fault motion. So yeah, because we have only the nearest neighbor interaction, which is not very quantitatively correct from the viewpoint of elasticity theory. But yeah, many people intended that the water play an essential role in causing slow earthquakes. So this redistribution might not be actually the stress transfer, or rather the redistribution of water pressure or the fluid transfer. Yeah, but this is just a guess, and we don't have any quantitative discussion on such interpretation.
It's not unreasonable, though, given the kind of the situation at subduction zones and so on, you know, with dehydration reactions and. Okay, well, thanks very much.
Thank you.
Yeah, thank you. Thank you very much. So thank you, Professor Takahiro Hatano, for your nice presentation. So with this, I want to move to next speaker. Next speaker is Professor Stephanie Santucci. So it's from École Normale Supreme de Lyon, France University, so Institute. So his topic is inertial effect on multiscale stick slip dynamics in adhesive tape peeling. So I request Professor Stefani to just go ahead for his presentation.
Hello everyone. Can you see my screen?
Yeah.
All right, so I can start. I will. I don't know if you can see my face, but my internet connection is very bad. So well, I'm just flashing and saying hello, but I will shut it now in order that it works. Okay, so let me start now. So, well, first of all, I would like to thank you for the invitation. I'm really glad to be able to show our work. And also I would like to apologize because I would have liked to listen to colleagues and friends, but I haven't been able to do that, and that is unfortunate. Well, so basically I will show you some experimental results that we have obtained in the last years, and it has started with the work of several PhD students. The first one is Marie-Julie Dalgue, who is now in Marseille as assistant professor, and Vincent Dezotti. And today I will essentially show the work of Vincent, and I will maybe discuss a bit the work of Hélène Piot-Durand, who is finishing her PhD right now. And this work has been done in strong collaboration with Pierre-Philippe Corté, who is in Paris, and in Orsay, and Loïc Vanel, who is a professor at Lyon University and with whom I've been working for many years. I am myself working as a senior researcher at the École Normale Supérieure in Lyon at the physics laboratory. All right, so a bit of history first. I mean, everything started, beginning of last century, and with this gentleman and Oskar Tropovich, who is was a pharmacist, and he invented, at that time, the first, maybe one of the first modern adhesive bandage, actually. And since then, this has led to this huge multinational German company of name Tesa, actually, and probably most of you have been using some of their roles. And okay, a bit later, actually, a lab technician in 1925 invented, actually, for 3M, the very first modern pressure sensitive tape, actually. And it was a masking tape. Actually, they wanted, for people who like cars with 2 different colors, in order to really paint accurately with 2 different colors, actually, they he proposed to use a type of cellophane ribbon on which he put a bit of glue actually. And this was the very first masking tape invented. Actually, the funny aspect is for the very first walls that they produced, the workers were not really happy with this system because apparently, I mean, 3M didn't put enough tape or enough glue on the tape. Actually, they started to complain, and this is a quote that I found in the net. Well, those workers were complaining and saying, "Take this tape back to those Scotch bosses of yours." And I don't know, I didn't know. Apparently, I mean, meant being greedy, actually. I don't know. It's a bit strange. But the funny aspect is that 3M decided to keep this name Scotch for their brand. Actually, now they are producing more than 900 different pressure-sensitive tapes, and even the colors of their tape are based on this very famous Scottish tartan. And actually, I mean, they are very extremely successful, as you surely know. And for instance, in France, I mean, every year, I mean, you have 35 million all walls that are sold every year. Well, the numbers are crazy actually, and this is just in France, for instance. So, and I mean, you have many different applications. I mean, and that's why I wanted to say that actually peeling an adhesive tape, typical wall that you have on all of us, we have one probably on our desk. It's therefore an experiment that all of you have done and have performed. And probably or surely you have already heard this typical screech sound, which is really annoying and disturbing. Actually, this is what I'm going to talk about today. Not exactly the sound, but this sound is the signature of the mechanical instability, also what we are commonly calling as a physicist stick slip instability. And finally, even though it is known and it has been studied for many, many years, like, well, so more than 50 years now, it is still nowadays a real industrial challenge. Actually, the noise can be, I mean, huge, big factory can become unbearable and above the levels that are acceptable for workers. Also, it can, of course, damage the adhesive, as we will see. And it can produce some shattering of the motors on big lines, and therefore, I mean, be a problem for production. So, how do we understand this, the origin? What is the origin of this of such mechanical instability? Well, it comes from the coupling between the typical behavior of the glue and the elasticity of the system that comes from the ribbon elasticity. And here, what I show you is a typical diagram representing the force, the peeling force, as a function of the peel velocity. And what you have two different branches, two stable branches, increasing branches here, and at where you have the stable peeling. But in a given region where the force is decreasing, you can observe a stick slip motion and this instability. Actually, well, indeed, when you are imposing a peeling velocity in this range, actually, it costs less energy for the crack in a way to advance faster and faster, and therefore that's the reason why the system is potentially unstable. And those two branches, I mean, and then start to oscillate between those two different branches, which also correspond to two different rheological behavior of the glue. I mean, at small peeling velocity, the glue behaves like a viscous rubber-like, as a rubber-like behavior, while at very fast deformation rate, well, the glue behaves as a glassy behavior, as a solid. Well, so far, or for many years, most of the characterizations have been indirect. So by ever measuring, sometimes on some systems, you could be measuring the force and the typical oscillations of the peeling force, or by directly, I mean, what I call post-mortem observation, looking on your system, on your tape, you could see some marks that are left on the band, and which correspond well, or also by listening to the corresponding acoustic emission. And I think this is a colleague, Matteo Cicotti in Paris, who has been working on that with some Indian colleagues of him, actually. Well, so the system we consider is our Drosophila, like my colleague in Paris is usually saying. It's the so-called 3M 600 tape. And why we use that is, I mean, it has been studied and used a lot in our community for maybe like 20, 30 years, and it has been largely characterized. So it's what we call a pressure-sensitive adhesive tape. It's composed of a thin, soft polymeric blend, the glue, which is about 15, 20 micrometer thick, behaves viscoelastically at small deformation, as I already mentioned. And it's deposited on a rigid backing, I mean, which has an elastic behavior, and the backing is about 30 microns. And this film has the following characteristic with this thickness, about 2 centimeters. And well, this is typically a desk roll that all of us have. Okay, and actually, the adhesive detachment and the steady detachment of this system can be described by a balanced equation a la Griffith. So this is, we can formulate this peeling problem as a fracture mechanics problem. And here is what I wrote, actually, this typical balance equation where you have the mechanical energy release rate equal to the fracture energy, which represent all the energy which is dissipated close to the crack tip, that is associated with the advance of the detachment front. And the mechanical energy release rate, we can obtain it from the work of the peeling force and the stored elastic energy in the system, which is this. Okay, and in the 80s, actually, Bartens and Mogis in Paris have proposed a quasi-static approach in order to obtain a prediction for the typical duration of a 6-loop cycle. And here is, well, I will summarize quickly their approach. What they assume is that this typical energy balance that I show here, which is supposed to describe the steady detachment, they assume that it is still valid during a 6-loop cycle. Then, by considering that you have a uniform stretch of the ribbon and that you have jumps and sudden jumps between those two stable branches, from measurement of the peeling force or the energy release rate as a function of the velocity here, they could obtain the prediction of the duration of the 6-loop cycle by just computing the duration of the 6 phase, actually, from their measurement. And actually, I mean, since the slip phase is really fast and the jump from the stick to the slip phase is also, they assume, extremely fast, they obtain basically the duration of that 6-loop cycle as a function of, for instance, here you see, it is proportional to the length of the ribbon and inversely proportional to the peel velocity. And they could validate their prediction with some experiments at different impulse velocity and from indirect measurements of post-mortem marks or some force oscillation that they could detect. However, I mean, it was obtained on a very limited range of peel velocity. And this, I mean, more recently, it appeared in some contradiction with some direct observation performed by my colleague now some years ago. I couldn't understand this, and this is the reason why it triggered our curiosity, and we started to work on that. In that case, my friend could measure some typical duration of the stick slip cycles that were constant and independent of the pill velocity. So this has already more than 10 years ago now, it has triggered a lot of experiments, and we started to develop some different setups in our labs. So, and the goal was actually to test the limits of this quasi-static approach. And as I will show you, we have revealed some new dynamic regimes of this peeling stability. And I will try to describe quite quickly this first part where we are peeling from a flat substrate at a fixed angle and at an imposed velocity, in order to show you the role of the ribbon inertia and the peel angle. But I would try to focus more on what we have done more lately, actually, and it was in Lyon with my PhD student, where we are looking at the detachment process, and that it's dynamic, but at very small scale, at microscopic scale. Okay, so here, first of all, I will just describe quickly this. This is the setup that was developed by Pierre-Philippe Cortet in Paris, and here you maybe, yeah, you see the video. Well, you don't see much actually. It's the fact is that in this setup, and this is quite amazing. Here you have a motor which can allow the peel to peel the adhesive tape, which is on a flat substrate here. At a given here can move. I mean, can be translated at a given velocity, and which correspond to the peel velocity that we are imposing, in order that the length of the ribbon here is locked in average, as well as the peel angle. And this is performed from very small velocity here up to 4 meters per second. So this is rather impressive what my friend has been able to develop. And here, I mean, we have changed the peel angle from 30 to 150 degrees and changed the peel length from 20 centimeters to more than 1 meter. All right, and what we observe from the side, I mean, typically the detachment process. And this is what I'm showing you here. Well, we are following the dynamic of this peeling point and its position as a function of time in the substrate frame. And what you notice here, even though we are imposing a given peel velocity, you see that the detachment is jerky, and actually you have this stick and slip phases where suddenly the detachment front advances very fast at a speed much faster than the imposed velocity, and you have steps where the front is not advancing. Okay, here I show you a phase diagram where we are in green. The green crosses correspond to the stick slip behavior, and so as a function of the imposed velocity and as a function of the peel angle. And what we have noticed and revealed here is that there is a strong influence of or impact of the peel angle. And actually, when you increase the peel angle, you are reducing the range of existence in terms of peel velocity of the stick slip motion. And actually, I mean, you can try yourself. Actually, this is well, for some given velocity, you may, I mean, by increasing the peel angle, you may feel stability. So, moreover, we have noticed that you have different, and it's a bit like what Atano has presented, Takahiro has presented just before, mentioning some different behavior of some stick slip events. Here, I mean, I show you two different cases Well, for instance, at small velocity and well, close to the onset of the instability and rather small P angle, well, this is a typical occurrence of the stick slip instability, the velocity as a function of time, if you want, and you have a very long stick phase and a sudden jump, very fast, up to 30 meters per second. That's what we could measure. However, we could notice that, I mean, this typical stick slip cycle, they can evolve actually. And when you go to very large P angle or large velocities, they evolve towards a quasi-sinusoidal shape, actually. And in that case, the stick phase and the duration of the stick phase and the duration of the slip phase are equal, actually. So you have two different behaviors. And actually, I mean, this first behavior was the one that could be explained, and that's why by Bartens and Mogis with their quasi-static approach. However, in that case, you see that, okay, the typical duration of the stick slip cycle is constant, actually. So therefore, I mean, we can understand now, well, now we don't understand yet, but we could notice, I mean, we could reconcile the two different measurements that were performed in the literature before we did those experiments. Actually, you see a typical evolution of the stick slip cycle and their characteristics in terms of amplitude and duration. And how can we understand that? So what we proposed at that time is to generalize this energy balance that I was showing you at the beginning, and by taking into account dynamical effects. And maybe I will come back a bit more later on that. But just, I mean, in our typical energy balance, a la Griffith, here, what we also include in this energy balance is the energetic cost in order to accelerate and decelerate the whole ribbon. But actually, I mean, this is, if you look at the numbers, you can notice that indeed, this for very high velocity, this this term is not negligible compared to the fracture energy of your system. By developing a bit this and computing those different parameters here, we can express and we can obtain an equation of motion for the position of the peeling front, x, here. And this is what we obtain. And actually here we have an effective mass of the ribbon here. It's basically the mass that we normalize by our geometry by the angle. And interestingly, what we have observed and is the fact that at large peel angle and at large peel velocity, the fluctuation, the fracture energy fluctuation, yeah, this term is negligible compared to the elastic term and the kinetic term. And therefore, I mean, you end up finally with a very simple equation of a driven harmonic oscillator, explaining actually why you obtain this typical quasi-sinusoidal shape for the stick slip motion, and we can also predict the typical duration of those inertial stick slip cycles, which became in velocity. So this is what we could show, and actually here, I mean, we could explain all the different regimes with a quasi-static regime and this inertial regime at large peel angle and large velocity. Okay, so this was a kind of long introduction to remind what we have observed many years ago now. But actually, and I will show you this, this video. Actually, so if you look at very small scales, so those marks here, the large marks, correspond to the typical stick slip marks that and corresponding to this stick slip motion that I was discussing before. But actually, if you look carefully, you can notice that in between, And even also on the substrate here, you can notice some small marks. So there is something at smaller scales that is going on. And so this is why, and also, I mean, we wanted also to understand the transition from the regular stable peeling here to the stick slip regime. And therefore, we have developed another experimental setup in my lab in order to focus more on what's going on at small scales. Right? And the setup is extremely simple. Here you have a microscopic glass slide, actually, which is transparent in order to see through and to look directly and to observe the detachment from during its peeling. And also we have another camera looking on the side, actually, and just looking at the detachment, but of the adhesive tape, but from the side. In that experiment, we don't control the peel length here, L, and the peel angle. However, actually, since we are looking at just very small scales, here typically the length of the ribbon is about 50 centimeters up to 1 meter, and we are looking at just an advancement of well, few millimeters. We can consider that this length and this angle will be constant during our peel experiment. The important aspect, again, I didn't mention that before, but we are using a high-speed camera in order to really follow the detachment process at a very high temporal resolution. And the last aspect, and this is a bit important, but a bit technical, but still very important, in order to have very reproducible results, we have we developed this trick. Actually, here we are peeling the tape from its backing. So actually, in order to do that, so therefore, when we peel the tape, it has never been unpeeled before, actually, I mean, from its form. So actually, how to do that? We using a scalpel, we cut 2 layers, and the first layer is attached on our glass slide here, and we are peeling the other layer here. This is really important because from the first peel, and when we unroll our adhesive tape and then putting back on the substrate, we may damage and change the behavior of our system. All right, so again, I want to focus on the transition to the stick slip motion. So here, this is a typical, the velocity of the front as function of time in the case of a regular peeling, and here in case of a typical stick slip motion. And the corresponding video are here. Well, the first one is quite boring, nothing is occurring. Here on the bottom, you can see. So you see you have this, here it's a stick face and here a slip face. And you can already distinguish actually some waves that are emitted and some type of, something is going on locally at the tip. I will discuss that. But first, I'm here two different impulse velocity. But what we could notice on a very narrow range, actually in an intermediate range of peel velocity, you could notice both some quasi-sinusoidal oscillation just at the onset of the typical stick slip motion. Okay, we're a bit surprised first, and so we therefore actually we have been studying this in more detail. So changing a bit the impulse velocity here, and so just below you have a stable motion, and just above you have the typical stick and slip motion. What you observe, so here we have just at the onset of the stick slip instability, we observe some quasi-sinusoidal velocity oscillation, and we can already notice that while the periods of those oscillations they seem to be constant, their amplitude keep on increasing with the impulse velocity. So here it was for those parameters with a rather large peel angle, and here I show you the evolution of the period of those oscillations, and as a function of the field velocity. And what you see here, so I report both actually. I mean, the circles here are for those oscillations, and you see that basically it's about a few milliseconds, or close to 2 milliseconds, and they are close to be constant. But suddenly, as soon as you enter the stick slip regime, the periods are much larger, and then they decrease with the field velocity, and they decrease like 1/v, as we could expect and notice before. Okay, and actually what you notice also is that the period of those oscillations corresponds to the period of the oscillations that we were able to characterize and predict actually at large velocity and large field angle. Yeah. So they correspond to this inertial regime that we were able to unveil at large field angle and large field velocities. Actually, there is a small also dependence with the field angle and the range of existence. Actually, we could detect those small oscillations at the onset for very narrow range of field angle, and the value of those periods depend a bit also on the field angle. Okay, how can we understand that? Typically, I mean, if we go back to this dynamical model that we proposed also to explain the inertial regime of the instability, I mean, by taking into account those kinetic effects, we obtain this equation for motion of the detachment front. Actually, interestingly, what we noticed already, and it was what I said, that at large field angles and large driving velocity, this term is negligible. I mean, comparing to kinetic and elastic effects. However, here it's quite interesting to notice that if we can neglect also, but not for the same reason. You have the same consideration, but it's relevant just instability and onset, because I mean, doing the fracture energy as a function of the field velocity, or if you want, we obtain it from the force velocity curve. Just the onset of the instability corresponds to the maximum of this curve here, and we see that you have a small variation here, and meaning that this just onset of this, you can neglect this fracture energy fluctuation close to the onset here, and therefore, I mean, as you one of the peeling length and the peel angle is constant, but we have a uniform stretch of the ribbon, and that we have weak fluctuations of this fracture energy close to the maximum here, and that we have small oscillation of this amplitude here. We can simply obtain a prediction of those oscillations in our geometry, and even we can also predict the evolution with the field velocity of the amplitude of those oscillations. And in that framework, I mean, we could show that actually the triggering of this instability appears as a supercritical bifurcation. Okay, so Vincent could perform some this analytical resolution, but also, well, with all those assumptions, but also he could numerically resolve this equation, and this is what you obtain, for instance, for the period of those oscillation as a function of the field angle. Here, this is the numerical resolution is in blue. His analytical prediction is in the dashed line, and here the squares correspond to our experimental measurements, which are rather in good agreement. And moreover, here I show you the comparison with, I mean, this is the amplitude of those oscillation as a function of the velocity, or as a function of the distance to the maximum the critical velocity, which corresponds to the onset of the instability. And what you see here is that you have this typical power law behavior, or this growth as a square root of v minus vc. Okay, so this was for the oscillations, and now let's move to what I call the multi-scale instability, because indeed, and already you can see it from those two videos that I'm showing on the top and bottom. So for two different imposed field velocities. So here, I mean, again, I show you the evolution of the position of the detachment front as a function of time, and what you see here. So we are in the you have the slip phase and the stick phase. But actually, if you zoom in and look carefully, and this is what we did during this experiment, at the evolution of the detachment front during the slip phase, you observe that okay, the detachment advances, or the front advances by steps. You have a step-like motion again, or micro stick slip motion, indeed at very small scales. And interestingly, so this occurs during the slip phase of the macroscopic instability here. But when we are peeling at even larger velocity, and this is this video, you see that this micro stick slip motion occurs continuously. Actually, you don't have so macroscopically, it seems that the front here at this imposed velocity, the advancements, if you look from at much larger scale, microscopic scale, the front advances regularly, but at microscopic scales, it advances by steps. Well, when I say microscopic scales, it's so you have jumps of about 100 microns, and typical microstick phase of few tenths of microseconds. Okay, so what is it? This microstick slip instability. So now I will show you several characterizations and many videos. So in order to look, well, here you have the videos. But I increase quite largely the frame rate of our very nice camera. So we are recording, I mean, the advancement of the detachment front at 700,000 frames per second. But also what I did here, I increased, I mean, the size of the region that we were imaging in the y direction. So here it's just few millimeters, 4 millimeters, but I reduce a lot. Therefore, I mean, because I mean, it would have been very nice to have a larger size in the x direction, but this is a compromise at those very high velocities. So let me play again what we observe. Okay, what you see actually is that the detachment front is occurring by you have transverse cracks actually, and so you have a propagation, a transverse propagation of a kink actually, which is indeed, I mean, the macroscopically the front propagates from top to bottom. It is like you are pulling directly on the tape, but you see that the tape detaches by triggered from the side. You have a kink, and which propagates in the transverse direction in the width of the tape. And so this is clearly, I mean, a dynamic rupture instability. And actually, what we were, since we were looking at not at as smaller scale in the y direction, actually what we mentioned as the micro slip phase was the width of this kink actually. So if you look also from the side, what do we observe? So this is the stick phase, and here the slip phase. So accompanying those micro slip events, what you observe that you have an evolution of the curvature of the ribbon, and you have sudden jumps in this curvature. Therefore, you have sudden release of the bending energy of the ribbon. And indeed, what you can see, so this is another video, what it was not meant on the purpose, but because it was not perfectly focused on the on the ribbon, you can see actually that the microslip duration is fixed by the period and the velocity of the bending waves, actually. That is released. And typically, the velocity of this transverse kink is around 600 to 900 meters per second. Well, which we were really happy to be able to observe it directly at those small scales thanks to our nice camera. So let me characterize a bit more this microstick slip motion, and what I call microstick slip is just, I mean, we are just focusing on one given position at the longitudinal position of the detachment front, and we could observe indeed this jerky advancement with small jumps, AMSS here, and this small period of rest just preceding the jump here. And we have Vincent and Hélène, they have performed many experiments at different peel velocity, peel angle, peel length, and here I will show you the results of several thousands of microstick slip events. So what do we observe? The amplitude of those jumps, so the width of those kinks. First, I mean, here is the amplitude as a function of the period just preceding this micro jump. It increases non-linearly with the period, but it is independent of the peel length. Okay. It seems, well, here what we see again is the same for a given length of the ribbon, but different peel angle. And you have slight will off on the range, well, this is more evident, and a bit on the amplitude of this micro jump. And here you see what we are measuring typically something around, well, from 50 micron up to, well, 250 micron, the width or the amplitude of those jumps. So if I show those results in a log-log scale, what you clearly observe that you have a kind of scaling law and a scaling behavior between the amplitude and those periods here, and it appears that the amplitude of those jump goes like to the period with an exponent 1/3. Again, independently of the length of the ribbon, and there is a bit of an effect. It seems that the effect of the peel angle is more, well, it seems to appear on the prefactor of this scaling law. And here's what I'm showing actually for a given period. I showed you the evolution of the amplitude of those micro jumps as a function of the peel angle, and you see that you have a small decrease. Okay, so we have seen that those micro slips were strongly related to a release of the bending energy of the ribbon, and therefore, I mean, we decided to modify the bending modulus of our tape, and how we did that by simply gluing several, well, increasing the effective thickness of our adhesive tape. And since the bending modulus goes like to the cube of the thickness of your tape, so, and this is what I show you here, the amplitude of those micro jumps as a function of the period for different numbers of layers glued on top of on the backing of the tape. And what you see is that you have a systematic increase of the amplitude of those micro jumps with the bending stiffness of our system, while the typical scaling law and scaling behavior that we could notice before for one given backing, it appears to be still valid. It's a bit more noisy because, of course, I mean, the way we developed and we prepare our system, but for larger and larger or thicker and thicker tapes. But still, actually, so again, the scaling between the amplitude and the period of those microslips goes like this, and the prefactor seems to be dependent also on the bending modulus. Okay, so again, how can we understand this? And we propose again to develop a local energy balance during considering this microstick slip cycle. And so what do we consider? Typically, during a microstick, we have the glue is locally stretched. So you're storing elastic energy by deforming the glue. And also we, of course, I mean, we have seen that, but the ribbon, I mean, is banded actually. So you're storing elastic energy both by stretching the glue and bending the ribbon. And what we will consider here is that the microslip will suddenly occur, and we see that, well, it would be a microslip of a given size. It will, so we assume that this microslip will occur when the glue will be stretched up to a critical length G. So when we reach this critical length, or critical deformation of the glue, then suddenly we have this microslip. And therefore, by considering this, we can write this local energy balance here. Here's the bending energy of the ribbon that is stored during the micro stretching of the glue, and this is the fracture energy here of the adhesive substrate joint, the jump of the microslip, and also what we are going to add again, where we have this generalized Griffith approach to include dynamical effects. And here, I mean, this term, EK, is the excess of elastic energy released, but we convert it into kinetic energy, and kinetic energy increase, but the tape will locally apply during the microslip. Okay, so again, this is a generalization of the Griffith approach, and it was proposed, somehow it is similar to this Mott approach to describe dynamic rupture processes. So this fractures, this effective fracture energy of our adhesive substrate joint, it has been proposed both theoretically and also experimentally to correspond or to be equal to the typical integral of the stress strain curve up to a critical deformation. Here, I mean, this will correspond to D actually. So this parameter D is actually crucial nowadays, and in order to really understand well, the detachment process. Okay, but well, by saying that, actually, then we can, those two terms here, the elastic energy which is stored during and which is accumulating in the deformation of the glue, will be fully dissipated when we have the microslip and when we have the detachment. And therefore, I mean, those two terms are equal. And finally, so with our local energy balance, we end up just by having a conversion of the bending energy, which is stored during the stick phase, the microstick phase, and which will be converted into kinetic energy, really, in the microslip phase. By computing those two terms as a function of the parameters of our system, and notably the amplitude of the microslips and the typical curvature here, and therefore you can relate it to the bending modulus of our system. And here we can also express the kinetic energy here as a function of the amplitude and the period of the microstick slip. We can have a prediction of the amplitude of the microstick slip as a function of their period. And what we obtain here is this typical scaling law with this scaling exponent, 1/3, which is already, you can notice it is very close to what we could observe experimentally. But also you have a prefactor here. And the prefactor, I mean, you have a dependence with the P angle and the bending modulus, and also the mass, well, the leaning mass of the ribbon. With a given exponent, which is very small here, and directly I can tell you that's why it was not easy to notice and experimentally and to observe experimentally the variation of the impact of the P angle actually on the amplitude, but still. Okay, so if I compare this to our results, and here I'm showing you the amplitude of the microstick slips as a function of the period preceding jump, and here I renormalize by this prefactor here, and so you obtain this scaling behavior, and this is for experiments performed at different spill angle actually. And what you see is that by doing so, when I renormalize by notably this 1 minus cos theta to the power 1/6, so here you clearly improve the collapse or collapse well, it allows to collapse those various data. And the important aspect is that I mentioned that we had this using our data, we can extract this value, which is found to be close to 5 microns, which is actually extremely, well, I wouldn't say in good agreement because it's really difficult for us at both scales to directly measure this value, but it is close to our resolution, and it is compatible with direct side observation. At both speeds, because this microstick slip instability occurs at very high, large field velocity, the glue, we don't see, we couldn't measure a strong deformation of the glue, and this is highly compatible. Okay, so then, I mean, by using this value of G, I mean, and I can plot here the prediction of our model, but here I show it for taking into account the variation of the bending stiffness, and as well as the variation of the linear mass when we were gluing several layers of backing. And what you see again, you can collapse all your data. And if I show you it in a log scale here, I mean, for all our data, you can see that our prediction is rather good. Okay, so with that, I will summarize all our different observations. So first of all, maybe an important and main point is the fact that the typical stick slip instabilities that have been known for many years when studying the detachment front of an adhesive tape. Actually, it is composed of two different instabilities occurring at two different spatiotemporal scales, and have different control parameters, different weight, vertex distance, and characteristics. But actually, I mean, the typical stick slip instability corresponds to the occurrence of those two instabilities occurring at the same time, actually. And importantly, to understand and to fully understand the behavior of those two macroscopic and microscopic instabilities, it is important, well, it is crucial to take into account kinetic effects, as I have shown you. So for the macro instability, we have observed and revealed a novel dynamic regime occurring just at the onset of instability. So the transition from a regular to a stick slip motion, which is composed of quasi-sinusoidal oscillations of the detachment from velocity. And our dynamical model can predict their period and amplitude and their evolution with the P angle. And as such, the triggering of the stick slip instability appears as, well, can be interpreted as a supercritical bifurcation. And for the microscopic instability, we we could have shown that it's a clear dynamic rupture instability with the regular propagation of transverse fracture kinks, and which corresponds to the periodic release of the elastic bending energy of the ribbon. And our scenario proposing a conversion of the bending to kinetic energy allows to predict the scaling behavior relating amplitude of those micro jumps and their period. Okay, but still there are still open questions, and even though we are not really focusing these days on that, well, the physical origin of those kinks, well, we are still wondering some aspects of that. Well, the fact that they always occur at a given velocity threshold, this still remains to be understood. But maybe I would like just to mention a few very quickly. I'm about to finish. That Hélène, my PhD student, is working on right now, actually, and she until now we have been studying the peeling on a smooth, homogeneous substrate. And actually, Hélène, she has been studying now micro textured pattern, actually, and ever rigid or soft. And interestingly, what she has been able to show that by notably changing the modulus, the elastic modulus of your substrate, having soft substrate that can deform, you can strongly tune the adhesion level, but also you affect the instability, and in a way that we can eventually control it. By eventually introducing some defects on the substrate, some texture, you can either trigger the instability or you can completely make it disappear. So we have observed that, and we still need to understand those results. And the last thing that I would like to mention, and this has been done in nice collaboration with my friends and colleagues in Strasbourg, so during the PhD thesis of Tom Vincent Hospital and Renaud Toussaint, and also with the Knut Malloy in Oslo. Actually, I mentioned that because it's a teaser for the next talk of Renaud. Actually, I'm sure will describe those aspects in more detail. But actually, I mean, what has been nice, we have been able to demonstrate, and thanks to the theoretical and numerical work of Tom Vincent Hospital, to show that the triggering of the stick slip instability could be related to a thermal, I call it thermal weakening mechanism. And here, for instance, what I will show you is we have been able to, using an infrared camera, to follow the increase of temperature locally at the tip of the detachment point. And this is what you can observe here. So during the stick phase here, thanks to this infrared camera, you can notice when those reddish, yellowish color correspond to a strong, an increase of temperature of some degrees during the stick phase. During the stick phase, I mean, the infrared camera is not fast enough and is not able to give something, or apparently this camera says that there is no increase of temperature. But this could be discussed. But actually, so when you are pulling on the glue, you start to increase locally the temperature, and this increase of temperature is probably the origin of the triggering of the stick slip instability. And I will not describe this, but this is what Renaud will explain you. But Tom actually has been able to predict the whole curve that I was showing you at the beginning, which allows us to explain the stick slip instability. So this is reverse. This is the velocity as a function of the energy release rate, and he is able to describe and the various different regimes that we have been measuring. in this taking into account these surfaces and the local diffusion of temperature that is created at the tip. And with that, I'll let you can have, I will stop here and just mention that most of what I've been explaining today is published in those journals, in those papers. But if you have more questions, don't hesitate now. And I thank you for your listening.
Thank you so much for the talk, Stefane. So now it is open for discussion. Is anybody has questions, please? If anyone has questions, please feel free to ask. And meanwhile, I'll just oh, okay. Takahiro, please go ahead.
Yes. Hi, Stefan. It's a very...
Hello, Takahiro.
Yes, I have just a naive question. So the tribal luminescence is a very interesting topic to me. And it's in this kind of phenomena, the temperature can be very high, but it's very locally, I mean, a very narrow area.
Yes.
Only a very narrow area can be very high temperature, but the other part, it can be ambient temperature. So in that cases, how can you measure the temperature precisely?
This is an extremely good question, actually. Actually, I mean, today, well, these days, together with Renaud, Tom, and Renaud and are developing some theoretical and analysis of that. But us in Lyon and with Loïc Vanel, we are currently trying to develop different experimental techniques in order to be able to measure those things.
Maybe I...
Takahiro, can you hear his answer or?
No, I cannot hear Stefan.
Me neither.
Okay. Maybe,
so I think he has some internet issues, maybe.
Yeah, sure.
Stefan, can you hear us? Because we can't hear you. He is disconnected.
Maybe in the meanwhile, I can say a few words on the topic, if I
Yes,
may.
please.
There is Renaud. So the funny thing with the infrared camera, the video that Stefan showed you, is that the red parts, the hot parts which are measured, are rather in the slow stages, not in the fast ones. And in the fast ones, that's when you have fractal luminescence. So it goes out of, when you have fractal luminescence, it goes out of reach for an infrared camera, but you can measure it with an optical camera. You can even see it in your eyes if you go in a sufficiently dark room. So indeed, the infrared camera pixels correspond physically to something which is large enough, usually a few hundreds of microns. Whereas the zone where we predict that you have something very hot that gives fractal luminescence is much smaller. It is typically tens or hundreds of nanometers. So it's much smaller than a pixel of infrared camera, which doesn't record directly the very hot temperature at this tiny zone. But what we can do is, since we predict the temperature in the fast stages and the size, I mean the temperature variation in space, so we have the, we can compute how much power is emitted and also the spectrum and the main waves which are emitted, the main wavelengths which are emitted. So these main wavelengths which are emitted corresponds to the visible light that can be seen in fractoluminescence with the black body radiation. And it also corresponds in intensity to the intensity that can be captured with an optical camera. If it answers your question.
Yeah, thank you very much. Yeah, that's yeah, what I wanted to ask. Yeah, thank you.
Thank you.
So, yeah, we can't have any more questions, I guess, because speaker somehow, I think he got disconnected. And also, we are on time. So at this point, let us take a short break. So shorter than usual. So usually we take half-hour break, but today we will have a 15 minutes break. So please be back in about 10 minutes or so, and we go to the last session of the conference, where first there is a talk by Renato So, and then we'll have some concluding remarks by Professor Bikashti, and others can join in as discussions. So yes, let's take a quick break for about 10 minutes. Stefano is back. He's trying to connect. Sorry, Stefano, we lost your connection. Hello? Yeah. We lost your connection. Yeah.
I know. I'm very sorry. I would like to apologize. Well, I had to restart my computer. I lost completely everything. So.
Thankfully, Renaud was there, and he answered the question that.
Okay, so probably must have said that we are using some particles that are synthesized by some chemists. Also, we're trying this novel technique that will actually, this type of particles they can emit light in a given at a given wavelength, actually, which depends. I mean, the emission spectrum depends a lot on the temperature, and therefore this will allow us to be able to measure quickly some local change of temperature at very small scale, actually close to the crack tip. And but it is exciting, but it's a real challenge to be able to perform such measurement. Thanks a lot, Takahiro, for this question.
Thank you. All right. So thanks, Stefano, for this wonderful talk.
Welcome.
Thank you. And as I was saying, so we'll have a quick break, and we'll be back in about 10 minutes, less than 10 minutes, for the last talk and some concluding remarks. So yeah, please be back.
Well, if anyone wants to ask me or send me some questions,
yeah,
and don't do that, please.
you can. So yeah, I mean, if anybody has any question, they can simply ask now. They can write in the chat. It's all fine.
Or later, yeah.
Or later, doesn't matter. Yeah. Okay.
पौने 5 का लगाऊं? 4:10 नहीं 4:05
Hello, can you hear me?
Hello?
Hello, you can hear me?
Yeah?
Good. Do you see my screen?
Pardon?
I wondered whether you see my screen.
Yes, yes, we can see your screen.
Yeah.
Okay, thank you very much.
Yeah. Just start in 2-3 minutes.
Yeah, no problem. I just wanted to set it up before the start.
It is perfect. We can see it. Yes.
Good. Thank you.
Okay, welcome back. And in this session, our speaker is Professor Renaud Dussault, is from University of Strasbourg and also associated with the Bohr Lab in the Oslo. And he will be talking about thermal effects in material failure. His breaking through matter is hot matter, how to predict material failure by monitoring creep, and how local heating impacts fracture. That's the main question. So yeah, please,
Thank you very much. So, and thanks for introducing me. Most of what I will present has been done by Tom Vincent d'Hospital during his PhD that he defended in November, and now he's a postdoc in Oslo in the Bohr Lab group. So, and some of it was started prior to that, but he was already associated to the work. So he was supervised by me, by Alain Cochard in Strasbourg, by Knut-Jürgen Molløy and Erik Flekke in Oslo. And some of the experiments were done in collaboration, or he used the experimental data of Stéphane Santucci and Loïc Vanel in Lyon, and some experimental data of Daniel Bonamy and Lamine Hattali in Saclay and Orsay. So the main question is how fast can subcritical fracture be? Subcritical fracture usually is a description of very slow fracture, but we will see here that actually we can describe also much faster regimes of fracture, still feeling some of the effects that are activation mechanisms. And it could be that, in fact, these activation mechanisms and how heat is released close to a crack tip play a very important role to determine whether a material is brittle or whether it's ductile. That's what you see here on the right graph of the energy release rate G on the lower axis and room temperature T0. And here what you see is the velocity of rupture in the vertical axis. And you see that there are hysteresis where the velocity jumps. There's a hysteretic loop where when you increase G, suddenly the velocity jumps to a very fast path. And when you unload, you have to unload further so that it goes back to the slow speed phase. On the left, what you see is an infrared image, a little bit like what Stéphane Santucci just showed you on peeled tape, but this is done on torn paper. The paper is torn at slow speed under a millimeter per second longitudinally, and we observe the fracture as it propagates, and you see that the fracture tip is hot. Pure riscalde will be what Galileo Galilei would say, and however it heats. So the general goal for studying fracture propagation is for us some fundamental goals like coupling heating and mechanics via chemical kinetics and statistical physics. Our motivations beyond academic motivation is also to care for the durability and safety of human-built structures and also of natural materials like bones, trees, or rocks that are important for earthquakes. And as it was mentioned by Takahiro earlier this morning, when you look at the slip along faults, you have both creep and what are now termed slow earthquakes, which don't radiate destructive waves, and you have also very fast stages with a large number of orders of magnitude of difference in the slip velocity. And when you go deep enough, instead of having some intermittent behavior and stick slip behavior, the material slips in a regular manner. So it could be that some of the considerations we have here could be at play also in this kind of setting. So first, I introduce you to some work we published in 2016. It is about, in soft matter, it is about fracturing paper. So you see we have put an infrared camera in front of a torn paper that was 10 centimeters large. And here you have a field of view, which is a few centimeters. What we wanted to study was the fraction of the released energy that was converted into Joule heating close to the crack tip. So we wanted to have we wanted to have a description of what happens. That's a little video for the process. So you see that the process is intermittent, and at the end, there's a crack that entirely tears the paper out. So here on the left, you see subsequent snapshots of this process. This is a time in seconds. And you have, what we look at is we transform these images into something where we look at the ordinate here, and the abscissa is actually the time since the crack tip, measured as the hottest part, has passed in seconds. And you see this decrease as the crack is going to the left. And this can be understood in a model which I will introduce just after as something where, in fact, you have a hot zone where the heat is released, and it's like a comet tail. There's a zone here where you have both heat diffusing on the sides and also heat diffusing towards the surrounding matter. What we do also is that we monitor the hottest tip position as function of time, and you see that towards the end this went much faster. So it's usually by looking at this tip position, we see something that propagates at a velocity which is around a millimeter per second, and sometimes it jumps to several centimeters per second. This can even stop before entirely tearing the paper out. So you have this typical crackle when you tear your paper. And here we measure force and displacement, which informs us about the mechanical energy that was put in the system. Here, what you see is the temperature elevation in this kind of experiment as function of the lateral position with respect to, so in a direction which is transverse to the main fracture direction. So you see that initially everything is well centered, and then it diffuses away. When we take the integral under this curve, we can see that this integral is behaving as an exponent of time, because here you have a log. Here I is the integral under this curve along the profile. And this can be directly understood as a linear coupling with the heat bath around the paper sheet. And by looking at the intercept at time equals 0, we can know how much internal energy rise was deposited by unit lengths by the fracture process. So this gives us an estimate of the term going into Joule heating. And we can compare this estimate to the term that corresponds to the energy released as the crack progressed, because we have monitored force and displacement. And by taking the ratio of one over the other, we found that usually in cracks, you have something like, you have a ratio alpha, which is usually around 12%, I mean 10 to 15% of the energy which is converted into Joule effect. But we had the surprise that when the crack goes fast, this jumps to a higher value, typically more around 50%. This can be understood with a very simple model, where if we consider that the crack goes at a certain speed v, and that the energy deposited is deposited within a zone which is of typical size L, then we write delta T, the temperature elevation, with respect to the room temperature, and we have a diffusion equation that describes the heat propagation, where D here is diffusion constant for heat. And here we have a loss term that corresponds to the diffusion and loss in the transverse direction, because this is a thin material, so it loses energy with it loses energy into the surrounding air. And here we have a source term. So this source term is proportional to G, the energy release rate, times V, the velocity of the crack. And to convert this part of, so it's only a part of the energy released, phi, which is between 0 and 1, is transformed into Joule heating. So the rest will become damage, dislocations, emission of mechanical waves or other types of waves. And underneath, what you have is a term rho C, which is for the volumic heat capacity of your material, and pi L squared just says that actually this term is on in the yellow region and off on the rest. And the integral of this term, so this is this term times pi L squared, it should be equal to, when you convert it to energy, it should be equal to phi GV. So by doing numerical simulations of this kind of thing at constant velocity, that's what we obtain for a typical temperature elevation. And we observe that when we go fast enough, actually, if we use for L the size, we can use either the length of a fiber or the thickness of a paper fiber. If we put the thickness of a paper fiber, that's when you have a knot that forms, and it's very difficult to unbreak it, to break it. So if you need to break the knot rather than untie it by reptation, then this model with the physical parameters of paper predict a very high elevation of temperature on the back when you start to have things which are of the order of micron. And this is consistent with the temperature where paper starts to auto-ignite, where you start to have oxidation of paper. And if you, then that will give an extra release of energy due to an exothermal reaction on the back of a fiber. And if this extra release of energy has to travel across a fiber thickness in order to soften the material ahead, the time it takes to travel across by diffusion will be given by square root of d times this size. And then if you advance by one fiber length every time you reach that, you obtain a certain velocity for d over L. And when you plug these velocities, that's more or less what you observe for the fast stages of crack propagation. If you look at how much extra energy is observed when the crack goes fast during the fast stages, you also observe something which can be compatible with the extra energy you gain from this exothermal reaction. So it could be that there's actually this process happening in paper when the crack goes fast. So here you have again a simulation where you don't go too fast. V is 1 centimeter per second. You have some values for G, phi, and L. And when you change, what did we change here? We change the parameter d over v square, and you obtain something that goes much faster. And if you can actually measure in the simulations the tip, the maximum elevations around the temperature elevation around the tip as function of crack velocity. This is a log-log scale. And you see that everything is parallel here. And you reach a maximum value, which is depending on the significantly heating zone size. So the smaller your heating zone, the highest is your temperature elevation. And it's easy actually to derive asymptotic expression for this plateau here and for the scaling relationship here. Here what you have is in fact that the quantity of energy transformed into Joule effects per unit time. This is phi times G times V. And this diffuses into a zone which is set by the skin depth of the heat diffusion. And the skin depth of the heat diffusion, delta, it is square root of the diffusion constant times the time where something is heated because it passes. So the time where something is heated goes like L over V, where L is the size of the process zone. So when you deposit this into a term of, at low speed, you deposit this term, H here is the thickness transverse to the system, into a zone of radius delta, you obtain this phi GV over lambda, which is this dotted line. And at high speed, you don't have the time to diffuse heat out of the zone where it is created. So basically, the internal energy is deposited into a zone of size L, and you obtain phi GV over pi rho CL. This is these two horizontal lines independent of V for two different L's. So you can do that for different values of L. And in the particular case of paper, you obtain what I told you, that if you use an L, which is of the order of thickness of a fiber, you reach for fast velocities a temperature which is close to this one, which is famous Fahrenheit 451, the oxidization of paper. But now we want to go beyond that. So I'll show you here mostly some things that have been published in Soft Matter in 2020, the paper that Stefan just mentioned earlier today. So we consider an activated process, and we say that the velocity of a crack is equal to the typical size of separating two neighboring molecules times the thermal vibration frequency of a thermal bath times an Arrhenius law exponential of minus a gap in energy. The gap in energy it requires to totally break a molecule divided by Boltzmann constant times absolute temperature. So this can be written like this. If U is the potential energy of a deformed molecule, UC is the total energy you can put into it in order to break it. And this translates into macroscopic parameter because U is proportional to G, the energy release rate. So there is a proportionality constant alpha square between the two, which is a small area. And we can express V like this, where V0 in fact is this size times the thermal vibration frequency. If you have something that propagates very fast and breaks every molecule, you will have the fastest mechanical waves that can exist in your system. So V0 here is of the order of the mechanical wave speed, the Rayleigh wave speed. Up. So we couple heating and mechanics via physicochemistry, and we say that V is V0. Here we say that T actually is the ambient temperature, but when you go fast enough, you get this rise in temperature, the Joule effect that makes delta T becomes larger. So when we pull over a system like this, that's a 1D system, you see, and we can compute what is G from U of T here. So we bend more and more the plates, a little bit like Stefan's spill tapes. And we compute what is G from the thickness of the bent plates. It's shear modulus and the arm of length A. And we plug it into G here. For delta T here, either we put it to 0 or we put it to something where we take into account local heating. For GC, we can consider either something homogeneous or, for example, a Disorder landscape that corresponds to a quench disorder in the material properties. Here, what you see is the position A as function of time, and here you have in this disorder landscape as how A advances in a system where delta T is 0, there's no heating. So it slips on the weak locations of G, and it's sticked in the tough location when G is larger. You can see here. And when we plug in heating and we put L with different sizes, here we have L 50 nanometers, that's the red curve. You start to have, due to heating, sometimes the crack goes faster. With even smaller heating zone sizes, these jumps are larger. And for even smaller, you can have very large jumps where the temperature is much higher during these large jumps. And afterwards, you have to wait for a certain amount of time until you reload your front, because this system is done in a setup where U is increased linearly in time. If we put a rectangular asperity, it's like putting an obstacle. So as function of position, you see the value of GC that we put. That you obtain for the crack advance. It sticks into the on the obstacle, and if the obstacle is small, here 20 joule per square meters, it goes through the obstacle and afterwards starts again with the same kind of speed. If you put a larger obstacle, you have to go further before you will break over it, go fast, and go back to the imposed speed. If you compute G in the same simulations, that's what you obtain. For a small obstacle, you have this, larger obstacle, you have that, very large obstacle, you have this. And you can compute a stick time and an avalanche size. If you have no thermal weakening, basically it will take you, if you have, sorry, here these are cases with thermal weakening. So if there is no very large heating, you are in these regimes. But if you go over if you start having a very large obstacle, what happens is that when you get out of your system, of your obstacle, you jump and you stay hot until you reach a certain characteristic G stop. And this heating starts when G, just after you pass the obstacle, reaches a certain characteristic G avalanche. Otherwise, you did not heat significantly and reach back the same characteristic value of G. So we want to compare this system where we have put, you see the Arrhenius law for the velocity as function of local temperature and value is computed from the tree and the extent of the crack. And the heating is simply from the model that I described, the model which was, yeah, this one. Either you take the numerical values that you have along the points, or you take the two asymptotes, but it gives the same type of results. And when you do this, you can compare it to experiments. For example, the experiments that Stefan Santucci just mentioned. So you unroll a classical tape like this, this kind of tape. And here you have points with that were measured by Barquin et al. In '97, and other points that were measured in the group of Stefan and Loic. This is Marie-Julie Dalb, that was the first author, who was a PhD student with them. Here you have the velocity of the crack front as function of the energy release rate. This is in linear scale, and this is log scale. And you see that the crack goes slowly, but sometimes it jumps to a fast dynamic front that goes several tenths of meters per second. Here you are more in the range of centimeters per second or below. And if you impose some velocity, which is in between a few tenths of centimeters per second, like what you do with your hands when you pull fast enough, then your system is unstable. So you have a hysteresis. It goes between the slow branch and the fast branch. Here you have a stick slip. You see velocity jumps at fast values and goes back down, and fast values and goes back down. And that's the screech that was mentioned in Stefan's talk. So here, Tom did the same experiment in Oslo in front of an infrared camera. And you see that it releases heat. You see also that there are fast and slow stages. You have breakage of fibers. Okay. You have also that it has been observed in papers by Chicotti et al., I think, and other people, that when the front goes fast, it emits light. When it's in the creep regime, it doesn't emit light. So that's the triboluminescence or fractal luminescence. Here you have an experiment that Tom did in the dark with a classical good reflex camera, and you see a blue light along the front during the fast stages. And it is also known from another publication in Nature that there was that when you do this kind of experiment in vacuum, it even emits X-rays. So when we plug in the theory with these two terms, you see an Arrhenius law here, and this temperature as function of crack velocity, that's what we obtain for the predicted velocity as function of speed. The parameters that are important here, which are alpha square and phi, they are actually obtained here. Alpha is simply dictated by the slope of this. Here, V0 and GC are enter only into the intercept at G equals 0. So knowing V0 from the speed of mechanical waves, you can measure what is GC, which alpha square GC will be related to UC, the critical microscopic energy you need to break a molecule for the crack to advance. And when you start to go here, your crack heats sufficiently with a sufficient temperature elevation so that it starts to be non-negligible compared to T0, the background temperature. So this curve, instead of having something which is, in log ln of V as function of G, instead of having some constant slope, alpha square over kBt, T actually starts to change. That's why you have this curvature. T gets larger. That's why you have this curvature to the left, and it gets hotter and hotter, and that's how you get something unstable. And here you have something that depends on L. That's when the skin depth starts to stop being larger than the size of the heating zone, the source term. So it depends on L and on lambda and C, because lambda and C just tell you what is the skin depth. So when the skin depth starts to be smaller than L, what limits you is the size of L. So the delta T that you are in this upper plateau, and then you increase again, and that's what you obtain for the prediction of the fast phase. So we have some models that predicts the color here is the log of delta T. You see that you have some moderate delta T, a few degrees when you are here. But when you go to the hot stage, you start to have thousands of degrees or even more over a very tiny zone, which is of the size of L. And this size L can be inverted to be only a few tenths of microns usually, or hundreds. It's a very tiny zone. And then this model predicts you the right shape with 3 or 4 parameters. And it's only this subcritical crack model. We don't have put inertia. Inertia plays a role probably there in this very fast stage, but you see that we get to first order even the fast stage, and that's over something like 7 orders in velocity or a bit more. Also, the temperature which is there, we already exchanged about that in the question previously. It is consistent actually with the wavelength which is observed and with the intensity of the light which is emitted during the fast stages. By knowing the thickness of the zone that emits because of its temperature, you can compute how much energy should be emitted, and that's in order of magnitude comparable both for the color and for the intensity. So that's here an experiment that was done in the Oslo group by Tom and collaborators. You will see some creep regime, which we have studied a lot in this group before, and also a fast jump suddenly. So here you have 2 plates, they have been sealed, annealed together, up the pump.
Oh, cool.
corresponded to some jump, and this jump actually could correspond maybe to something which is, you know, the classical sense of fragile rupture and something becoming hot. But that's something we want to investigate, like together, for example, with Stefan, that mentioned these special techniques that they like to use. So now we jump to another material, PMMA, not in the kind of experiments I showed you here, but in bulk PMMA. The group of Daniel Bonamy and Lamine Hattali, what they did was that they pulled some little wires across bulk PMMA, and they pushed with a cone into a little hole at different speeds. So they studied precisely the loading curve G as function of V over a lot of ranges of V in bulk PMMA. And they measured the velocity, not only the force time dependence, but also the velocity force dependence, velocity time dependence because in PMMA, as crack propagates, it breaks little wires, and they have a multiplexer to measure how fast it goes. And that's a prediction of the same model with these couple of parameters, which falls well with experimental points. Here we have taken into account for the very slow thing healing term in addition to the breaking term. And another thing is that it is known and observed already from some time. It was published by Daniel Bonamy's group and other people that there are these patterns in PMMA when you go fast. You don't get them when the rupture goes slowly. And the funny thing is that here you get a very high temperature, which is predicted. So this very high temperature is over very tiny zones. And in fact, when you look at what you have in the middle of these patterns, we discussed with Daniel, and it was not really mentioned before, but at the center of each of these zones, you have very tiny holes, which are the seeds for this secondary crack to grow in front of the main one. And these seeds, they have indeed sizes which are hundreds of nanometers. This could be sublimation bubbles in heated PMMA ahead of the main crack. That comes from this publication, Scheibert et al. Now we will see how this model, that's more theoretical. In this model, there is actually a phase transition, because here, this jump from low velocity branch to fast velocity branch and back with a hysteresis, this corresponds to a first order phase transition. But there's actually also a second order phase transition that corresponds to the end of this jump of these avalanches. So this could correspond actually to brittle ductile transition. You see, which is known when you heat a material. For example, when you go at the basis of the lithosphere, plates start to deform in a regular way and not they don't slip in an intermittent way. So it's important for natural systems. It could be important also for others, of course, and unnatural systems. And in this, I'm just saying that the ingredients could play a role there. The geometry we use here is much simpler than the geometry in faults. So we did not consider directly the application on faults. That's something we'd like to do on the way along. So in the equations of the model, you had that V was an Arrhenius law of delta G over KBT, but T itself depends on V. That's the delta T part of T that depends on V. So when we plug this, when we actually put into our Arrhenius law how T depends on V, we can solve for, we have a straight line, and we have here that's simply the left term as function of the right hand term, and we obtain this kind of lines here. So when we start with when we start with a low value of when we are in a low value of G, there's only one point here which sets the velocity. When we have higher values of G, you have actually two solutions. So two stable solutions and one unstable solution. The V that we called V avalanche, V stop, that was in this system. We have G avalanche and G stop. This corresponds to large speed and a low speed. And when you go into an even higher system, we get only for G even larger than that. Oops, for G even larger than that, we are only in the fast regime. So these curves, they correspond to a motion, which is a hysteresis in G as function of V. You do hysteretic loops like this. When you are in the intermediate imposed velocities. And the distance between G avalanche and G stop that correspond to these two values. When you increase T0, what happens is that these curves are becoming smoother and smoother. And eventually the increase in temperatures that you have is not important. So these curves become with a maximum slope, which is smaller than the one slope here. And this G avalanche and G stop, the 3 points here merge into one and vanish. So what you have is a critical point. That's a representation of V as function of G and T0. And that's a little bit the same thing as what you have for ferromagnetic paramagnetic transition, for example, or an Ising model, or you have basically these two lines that merge, and at large temperatures, if you increase G, the only thing that you have is that you have V that increases, but in a regular way, it doesn't jump anymore. So the intermittency disappears. We can even compute the classical critical parameters, which is done in this physical review materials paper. And you have them here. Well, we computed them in a simple way, so they are close to some of the mean field models. But when you put in quench disorder, it will probably change. We'd like to apply this system to other materials and see whether, well, a lot of materials actually creep. So it means that when you impose a certain G, you get a certain velocity. This is published data in these different papers. So here that's for paper, here it's for quartz, here it's for titanium. These are very different materials. But in a lot of publications, people have looked at the velocity of a rupture front as function of G. And eventually, usually when G increases, suddenly it snaps. These are the red lines here. So you can compute from published data, when a material snaps. And also, if you are lucky enough, people have measured before that how V depends on G. So you have a creep part. And the question we ask is, can we actually infer just from the creep part the essential ingredients from such model, and from the essential ingredients from such model predict when something will break? So that's what we did. So this is in this paper here, which is which is just accepted. So it should soon be released. It is already available in arXiv. So in most materials, you have several creep regimes which are known. You have creep part 1, creep part 2. This is depending on the environment. Here, nothing moves. That's 0. In 1, you have something which is crack corrosion. It depends on how the material changes the chemistry at the tip. Here you have something where the material around, like a fluid or air, cannot reach anymore the tip of the fracture because it goes too fast. So you have again some linear regime in lin log. And then you have failure so the 3 is the one you have in vacuum. So that's how an experiment typically looks like. And what we say is that in our very simple description, when you take the log of V, it's a linear function of G plus something here which just depends on a couple of parameters. So if we can observe only one of the linear regimes, either environmental one or in vacuum, we can actually, from the slope, infer what is alpha square over kb T0, but we know kb and T0, so we'll have this alpha square. And from the intercept, by looking at the linear part, we will have log of V0 minus alpha square GC over kb T0. And V0 is actually the speed of the mechanical wave. So this will tell us something about GC and alpha square. And we can also plug in the thermal part and get compute GA from our models. So GA from our models, if we know lambda, we can compute also what is GA. That's a simplified expression for GA. The avalanche, that's usually what is called the macroscopic energy release rate. GC is a microscopic one because alpha squared GC, that's UCs, how much energy it takes to break a molecule. And that's what we do on published data. We invert that, we compute GC because we compute alpha squared and GC. And after that, knowing V0 and lambda for this kind of material, we compute GA and we compare GC and GA from this creep data. So that's what you obtain for many different materials. We have computed GC, we have computed the real GA, that's the one which is observed in the paper, where you have macroscopic break with you go into the fast branch, and that's the modeled one just from the creep observation. You see that these are rather close things. So here, as function of the experimental GA, you have the modeled GC. These are the yellow parts, so usually it's higher. And the model GA, these are very close to the straight line. So we have a rather good prediction, which is usually within less than 50% of the observed GA. Only by looking at creep, we can predict when this material will fail. And when you don't know what is your material really, because it's complicated, it could be an interesting engineering approach. Here, what you see is also the UC, alpha squared GC, which is computed from these different materials. This corresponds to the range of classical in electron volts. So this corresponds to the range of classical links in between molecules. I'll skip that. This is about the size L as function of the macroscopic process zone size, but basically it's typically 100 times smaller. And here, okay, I'll fast forward through this. That's parts where we put in GC, fluctuating GC, because so far it was not fluctuating. So when we have a fluctuating GC, we have non-straight cracks. So the local G here will be computed from Gao and Rice kernel from the macroscopic one plus the deformations of a crack in an elastic material. So when we do that, we obtain, so we compare to this kind of experiments. That's an experiment done by Tom in the creep section, but what we did was that we compared to the published data in Talakstadt et al. In 2011. And here you see this kind of, here you see a numerical model with the same ingredients. Here what we did is that we did not plug heating. So it's still the same model, but delta T is negligible. It goes slowly. So you see that the line progresses and we count how many times it stays at the same position, and the darkness you see here corresponds to how long the front has sit. So it's proportional to 1/V. So the light part is when the crack goes fast. And here you see afterwards a map like this. That's what stays if you have counted the local speed like this. And you see this map that encodes the speed of the front. From that, we can do the type of characterization that were done experimentally. For example, well, that's the average position of the crack as function of G. So we see that the average position of the crack also is an exponential of G. We published that with Olivier Langlinet in 2011. And then that's here you have a comparison between the simulations and the experiments from the materials that are best fit, material constants which are best fit between the simulations and experiments. So this is from these proceedings of Royal Society A. That's a probability distribution function of the local velocity, and this is close to the observed experimental one with a tail of probability going as phi to the minus 2.55. It actually says something about the width of the disorder compared to its average value. And sorry. So when you go further into that, Tom submitted something in scientific reports, it's in revision. You can look at other things. So this is still the same probability density function of the local velocities, but here you see the roughness, so that's the root mean square of the front height as function of the lag between 2 points along the front direction. And we observe two self-affine regimes in the simulations and in the experiments. And here you have the distribution of avalanche sizes, which resembles to some extent the ones that you have in the experiments. And further away along the road, we want now to plug both, you know, a non-straight crack, a variable GC, and an induced heat term. So that's just a glimpse of what you get when you do that. If you increase phi, you see that you have larger and larger zones, which are the hot avalanches. So these are different avalanches. That the avalanche is due to the change of GC and non-straightness of the crack. This is due to the heating. And you see that at a very large phi, you have very large avalanche, which are system spanning. Okay, you can also vary the disorder correlation lengths. So for uncorrelated or lowly correlated, you get that. If we put longer correlations in the disorder correlation lengths, we get more correlated avalanches. That's no big surprise. And here what we change is standard deviation of GC with respect to the mean GC. So when we get larger and larger, when we get larger variation, our system is more pinned and our heating is not so important. And if we heat the system, if we vary the ambient temperature, here we will increase it, you see that we get less and less of these hot avalanches. We are coming closer to the critical point, actually. And that's it. I just wanted to invite you to go and visit this great piece of art that is done from the experimental and simulation images we have produced in PoreLab, where the PoreLab people have done this virtual art exhibition. So it's at the address over there. And when you enter it, one of the little things that you can observe is some simulations. And I thank you for your attention. Do you have any questions?
Thank you so much, Renaud, for the talk. Now it's open for questions. So if you have any questions, please unmute and ask. Meanwhile, I just wanted to ask a small one.
Sure.
So when you showed that you are trying to predict the failure using the creep, which reminded me very much of what Miko was describing the day before yesterday. So I was wondering what sort of the error in that kind of prediction, if you want to make.
One of the things that you don't have is in the fast system, you don't have the inertia. So for sure, when you go close to the mechanical wave speed, you miss the terms that corresponds to exciting the mechanical waves. This is not because here the elasticity we have considered is quasi-static. We could have in the way we express G. But if you express G from the memory of your system, not only the G that comes from the boundaries, but also the deformation, which is due to the emissions you had prior to that, you should still be okay. Another thing which you are missing in this kind of model, for example, is the fact that our crack, I showed you essentially before the final part where you had a front, our crack was just a point moving in a given landscape. So you're missing the whole geometry of the line. And also when you go fast, your cracks, they branch because you actually release more energies that you can cope by just opening, breaking a single line or a line when defects around. So you will have this branching and you will need to put that into the description as well. But I think that it could be that actually you can still describe things with RNU laws when you go very fast and your system is branching out. But for that, you need to go into molecular dynamics or even quantum description, I don't know. But first with molecular dynamics, usually in molecular dynamics, people don't take into account the fact that their temperature is increased locally. They put their system in thermal bath, and they consider that they have a thermostat. But I think if you do the same kind of heavy molecular dynamic simulation with a coupled intertwined field, which is a temperature, knowing how much energy goes into heating and how much goes into creating defects, you can actually take into account the fact that locally the temperature can be very different. And there, I think it's okay to consider a classical Arrhenius law. So in this Arrhenius law, you get that if G is smaller than GC, you have this Arrhenius law. And when G is larger than GC, I forgot maybe to mention, what we say is, okay, we just go at the maximum speed. We break every element as we advance. Okay.
Yeah.
And it could be that if you have a more complicated description mechanically of what happens, you will also break several things, because you will have loaded many things, not only the one which is just ahead of your crack. You will, break at some points ahead of the main crack. So I think you can refine this, but the main take-home message is that usually we consider subcritical crack dynamics as something that only is relevant for creep and very slow crack growth. Well, all of this and this comparison says that maybe after all, it's not. We should take it into account also in the advanced methods that describe very fast crack propagation.
So that's what I was about to ask. So is in your case, the temperature variation is only in the process zone and not ahead of the process zone?
It's all over, but the only one we have considered is the highest temperature. So in the simulations, you see that we have a temperature elevation everywhere. But the one that dictates how fast we go, it is the hottest one, which is just on the where you allow your crack to grow. So we can compute very simply with neglecting how you move. When V changes, it takes a certain amount of time to go from a stationary solution of heat to another stationary solution of heat. So the temperature doesn't jump directly to the new stationary profile. By actually neglecting this transition time, that's how we obtain. So you see, we neglect these rays and we say that the temperature, the hottest temperature, is directly this straight line here when the velocity changes. And that's why we can compute very easily what is the maximum temperature as function of the velocity. So we can also do the modeling by computing the whole thermal field and let things crack all over. But then it's, for every configuration, we need to have the thermal field in all the space. That's much more costly than computing what is the hottest temperature, which is very straightforward. And okay. So you can run simulations, but it's very slow, and for tiny systems.
Sure. Any other question? Yes.
Hello. Yes.
Hello, Peru.
Hi. Hello. Thank you for this wonderful talk.
Thank you. Thanks for the invitation.
Reno, yes, I was wondering that your experiments have precisely shown that there's a very hot temperature zone in front of this subcritical cracks. But such maybe it is included only in the fracture process zone, a part of it. But its effect can be quite drastic. So I was wondering that what its effect can be in the engineering fracture mechanics, where this kind of a thing is generally not taken into account, or in LEFM, but of course in the subcritical growth. So can you do you have any point regarding this? And also I was wondering that what can be the effect of ambient temperature? Suppose the ambient temperature is very low or high, so that the energy is dissipated fast or cannot dissipate that fast, what can be its effect?
So if you have a different ambient temperature, the first effect you have is that the heating becomes not so important. So you go into this ductile, you go into this ductile behavior rather than the brittle behavior where you have jumps.
My point is that we know that brittlity or ductility depends on temperature.
Yeah,
so do you think that this can have some, it reflects on that?
Yeah, that's exactly. I mean, that's exactly the point in this.
Yeah, you mentioned at some point.
In this graph, you see, at large temperature in this kind of model, the two different values. So these S shapes for velocity as function of g that correspond to the fact that you have something brittle, basically, because here you go, you increase, and suddenly, poof, you jump to some much faster velocity. When you go at large enough temperatures, then the rise in temperature due to heating is not so important compared to the temperature. So these jumps disappear. And what you observe effectively is something that behaves macroscopically as a ductile material. So this is a direct prediction of this model that you have a brittle ductile transition. As for the other question, there are two ways in which we can infer the L size, the size where it's not the process zone size, it's the size where a lot of the heating source happens.
Right.
And we can compute it either from looking at what is the maximum. We can say that the energy release rate is related to sigma square over E, and we can use I think it's would be over there somewhere. I think there's a slide about that here. Okay. No, it's not written directly here, but basically there is when you compute what is energy, when you compute what is this alpha square GC, so UC, it will be related to you will obtain that you have a 1 over L term. You will obtain some terms that alpha squares, this alpha square that you can measure, it is actually size cubed divided by a certain L, which tells you which is a cutoff in the elastic singularity, and that's one of the ways you can compute L. And this gives you this thing which is tenths or hundreds of nanometers, and this is actually smaller than the zone where you start to have non-elasticity. And the zone the zone which is normally called the process zone, where you get out of the elastic behavior, it is when we compute what is the heating zone size as function of the macroscopic plasticity zone size, we observe something which is 100 times. We observe some linear trend between both, but they have a very large, they have a number of orders of magnitude difference. So the zone where most of the energy is dissipated in terms of heat, it's much smaller than the zone which is flowing. And there are many processes that are happening in the flowing zone. So it could be that it's only in the most intensively deformed part that you actually deposit a lot of heat. Then the heat will diffuse and you will have a hot zone which is much larger, but the source is actually much smaller. The other way to measure it is from this kind of curves. Here, the fact that the velocity actually this first L size is just due to the fact that this alpha here that we can measure directly because it's related to the slope. It is alpha is actually going like the square root of d cube over L, where d is the molecular size and L is the heating zone size, which also corresponds to this maximum of stress where it doesn't go higher. The other part where L is playing a role is that when the skin depth becomes of the order of the heating zone size, that's when this curve is going from the left to the right. And we measure, so these are two different ways of measuring L, and these two different ways are actually from this kind of series of points consistent with each other and giving the same kind of answer. And they're based on very different experimental conditions. You see here we have velocities which are microns or millimeters per second. And here this is about a branch where cracks is at the end of the instability and you go to the fast branch. So it corresponds in these speed tapes to 10 meters per second. And they both give you the same kind of answer. And it's very hard to observe because if that corresponds to reality, then we're talking about how to measure heating. I mean, these are indirect measurements because this is a theory, we fit it and it says, oh, L is very small. But this is another observation, the fact that we plug L as a thickness and this temperature, it gives us the right the right color and the right intensity. And yet third observation will be, can we directly measure a very transient, you know, for a very small amount of time, the temperature that you reach in something which is, you know, sub-micron, more like nanometric, when your crack goes through. So that's one of the things we'd like to do with Stefan Santucci and and these people. But this is just a goal. So far, it's not done. We also see that it takes 250 degrees to actually make to actually have flash heating in PMMA. So if these things, if these little nanometric things are flash heating bubbles that grow before they become cracks, it says that the temperature at some distance of the main crack has gone over this temperature of several hundreds of kelvins. So we predict that this can go even above 1,000. So it's consistent. In order of magnitude, these are not precise things. These are just hints that it could be, that there could be something there, because you don't observe temperatures when you go, when you are in lower, when you are in G's which are below, I think something around that value. The surface of the crack post-mortem is smooth in PMMA. It's only something which is observed when it goes fast.
Good. Yeah. Yeah. Thank you, Reno. It's a really wonderful observation. And it's very fitting for this conference because it is directly related to Griffith's energy. Energy balance. Thank you.
Thank you, sir. Is there any other questions? If not, let's thank Reno again. And I also want to thank all the speakers of the conference. And so now, before we finish, so can I ask Professor Prakash Chakraborty to give some concluding remarks about the conference? So yes, please go ahead.
Okay, so
do you want to share screen?
Yeah, you can. Yeah.
Yeah, it is. You can share.
No, I just want
yeah, please go ahead.
Okay, is it there?
Are you trying to share the screen? It is not there.
No, I'm not trying to share the screen.
Okay, then please go ahead.
Yeah, please. I have a little, but I mean, I think I can do without that. But yeah. So can you see me or?
Yeah, we can see you. Yes.
Okay, just a minute. I will have to check. Yeah. Okay. So thank you very much, and Shomo also for inviting me to conclude. Although there is not much to conclude. But it's a very nice opportunity for the last decade or so. These Fracmeets are being organized. I guess from 2012, it was regularly being done at IMSC, Institute of Mathematical Sciences, Chennai, by Purushottam and co-workers. And since 2020, I believe, for the last 2 years perhaps, FOMO is organizing in SRM University. It gives us a very nice opportunity to update on the latest research fronts in some kind of statistical physics of fracture, breakdown, earthquake kind of studies. And I have some worry about the pace at which these things are being done, and also lack of popularity among our the younger researchers do not have much interest or imagination about this future of this subject. So I will come to that. But before that, let me actually try to, in my way, I will try to say that this breaking of materials and strength of materials had been one of the earliest questions and still being asked as we are continuing. I must mention that the first very scientific study was made 500 years back by no less than Leonardo da Vinci. And his experiment was, well, the questions were these. Later on, Galileo, in few years, maybe some 70 years later, Galileo also joined. The question had been, why don't we see something like, big trees, bigger, even bigger. The tallest trees that are probably available are the redwood trees in California. They are about 300 feet. And then Amazon trees are still less, something like 200 feet. Why don't we have bigger? Why don't we have taller? Now, one question may be how to pump water, because the leaves are at the top, and you have to pump the water and capillary things, and then minor motors. This will be costly, and more importantly, there were no bigger animals to take the leaves as the food. So because the tallest, the fossil record says the largest dinosaurs had been also 85 feet. They could go up to 85 feet. So again, the question is, why then the trees went up to 300 feet? Because none of the animals were actually able to touch them. They could stop at 100, so they didn't. So they went up until what happened? Then, well, again, the animals, the largest we have today on Earth is, tallest is the giraffe. They are about some 20 feet maximum. Elephants are about 15, 18 feet in height, or kind of length. Of course, with trunk, it can go a little more. So take 10 more, 8 more feet or 10 more feet and so on. Even the buildings that we can produce today, the tallest is Burj Khalifa in Dubai, and that's about 2,800 feet. What's wrong? Are we, are the Khalifas, lost their money, kind of finished off their money, and they didn't have any further money? The idea is that with these materials, with the kind of fibers that the trees, these were the answers by Da Vinci. And Galileo also. Galileo had written about it. Da Vinci's idea was that somehow for each material, if you make bigger and bigger, the fracture stress or failure strength will come lower and lower. This is the very important problem we still try to kind of study in details. The question of extreme statistics. He had a nice experiment. The experiment was that, he took a, similar kind of wires of from same material and also from the same make or same furnace, same kind of procedure. And he found that, I mean, although it was never mentioned in his writings, that the elastic modulus seems to be the same if you increase the length of the wire. But it was clear that the tensile strength of the wire decreases as the wear length increases. And he had a kind of faint idea why this happens, because it's something like defects are more probable, bigger defects and weakest points have finite chance. I mean, the weakest point becomes, determines the strength, not the average defect kind of structure, which may kind of control the elastic property, which they didn't mention. But it was clear that he realized that there are some extreme events. Failure is an extreme event. And so what they are, both Da Vinci and more clearly later by Galileo, it was about 450 years back, it was clear that the tree size on Earth is limited not by any biological thing, anything else other than a mechanical failure problem. Similarly, the animal size, that it cannot grow much beyond some things, is because of the bones that are more or less the same. And with these bones, you cannot go up to that size, or you cannot continue. And no money, and also for the same thing, for the buildings, we have to change the way. With these, up to 10 stories, 15 stories, very nice. You go for bigger, you have. But then with these latest materials, you can go up to perhaps now 3,000 feet. You cannot go to some, 30,000 or something like that. For that, you need some other material, which we have to still develop. So that's the thing. We cannot construct unusually long bridges with the materials that we have now. We have a limit, and that's the thing that is determined by failure probabilities and this fracture strength of the solid. So these were 500 years back, and then there were not much of study which we know. Essentially, 100 years back, Arnold Griffith, in 1921 wrote this paper in Philosophical Transactions of the Royal Society. This simple Griffith criterion for extension or nucleation of a micro crack in a solid, assuming that you have one piece of one defect, or rather a very strong defect, long in some sense, a bigger size defect in the system, and others are somehow contributing to your elasticity. So he could map this problem of nucleate. That whenever there is a fracture, a micro crack will grow, just force conservation will not work, because at a sharp notch, you can have manifold increase of the stress, but that would not kind of cause the breaking, because you have, once this notch fails, there is a opening up, crack opening up, new surfaces are produced. That surface energy has to be provided. So the elastic energy stored earlier must be enough to provide at least the surface energy. That gave a very elegant theory of breaking, mostly in brittle materials. Assuming linearity up to the failure point, you could actually calculate the energy and equate it to surface energy. So it essentially energy went as the size square, and then volume proportional to the volume, and surface energy goes as the square of the crack. And so essentially it is square root of, and stress square. elastic energy will be stress square times strain. And so there was stress square was going as 1 upon L, or the length of the crack, the size of the crack, and so it was square root L. And that was, I mean, although it was very difficult to have micro cracks within the sample and then measure those days clearly, but it turned out to be a very accurate theory, and we had a long journey after that. After that, and we had discussions on Griffith crack, I mean, recent advances with many of these things with subsimilar structures and so on, and excellent discussion here. And then we had the fantastic model, very rich, yet so elegant, so simple, and that is the fiber bundle model. It was, again, in 5 more years, we have to perhaps celebrate. Maybe Fracmeet will again organize a special meeting on that. Frederick Thomas Spears published in 1926 in a textile journal. The journal is no longer there, this fiber bundle model. The idea is very simple, that you have these hook springs, hooks for the elastic part. I mean, you have a large number, macroscopically large number of hook springs hanging from a, say, rigid platform. You have another platform below, and in between there are many hook springs. Each, say, have the same or identical spring constant, but they may have, and then of course, and if the breaking strength of each of these spring is the same, then of course the bundle is trivial. I mean, of course, you put load on the lower platform and it will get all will get extended. Suppose this lower platform is also extremely rigid, there is no local kind of modulation, so it just goes down. The stress increase will induce equal strain because everybody has same elastic constant, and then everybody simultaneously will go past the their strength. So the entire suddenly the whole thing will fail. But that's the trivial thing. The idea was that suppose they are not. So what will happen? Because they are not, I mean, some will fail, and then depending on how this extra load, I mean, because once the fiber fails, the share that it was sharing, the load that it was sharing, has to be transferred to others because the total load is there on the whole bundle. So that sharing, I mean, and that was where the model became extremely intriguing when Daniel in 1945, I believe, yeah. In Proceedings of Royal Society, I believe. But anyway, he showed that, well, even for very rigid platform, the sharing will be equally among the surviving fibers or springs. So they have an extra load, and even if the external load has not increased, this will happen, and this may trigger further failure somewhere. And that failure may trigger further failure, and eventually the whole bundle may survive because everybody has a strength now above the load per fiber, surviving fiber. In that case, bundle has survived. Otherwise, it will go on, and then the avalanches will go on, and then finally it will break the whole system. A fantastically rich one, and there are so many studies now from physics side also, and almost I mean, and computationally so many studies. It's one of the richest condensed matter model, I believe. I mean, in simple, intuitively appealing, and yet and a lot of physics can be also physics of dynamics of cooperative dynamics of such systems, coupled systems. Then there were, of course, the statistics, extreme statistics were characterized, Weibull and first exponential, this double exponential Gumbel, and then that was in 35. Then 1951, Weibull came, and then all these statistics were identified, and then it was applied to these materials in about 80s. Before that, a celebrated model, I mean, well, earthquake everywhere. I mean, there were limited discussions, but Takahiro had a nice discussion today on earthquake models and also some dynamic studies. And Gutenberg and Richter actually gave a very important kind of law, kind of indicating that, of course, intuitively obvious that the higher magnitude, and these have been explained in lot of details by Takahiro this morning. But I mean, anyway, higher magnitude will be lower, higher magnitude earthquakes will be lower in number. That's intuitively obvious. But I mean, they showed a particular way how it goes down. And if it is translated into energy, from magnitude to energy, it will be essentially a power law distribution. So that was a nice and established story in geoscience or earth science. It's actually a macroscopic failure phenomenon. Then there was a nice model which has not picked up that much, but I mean, is so far the best, both laboratory for laboratory experiment as well as for numerical study, the Boris-Zubov model. That was in 1967. And so, and then it goes on. I mean, there are many things. After 80s, there has been a huge upsurge in fracture studies and so on. There have been many physicists, statistical physicists who have joined, and but still, I must say, I mean, one very, I don't know, kind of one pity I consider is that none of the textbooks in condensed matter physics in any kind of any circulation or major circulation. So textbooks which are higher circulation now, I mean, of course, Kittel is no longer alive, but say there are books like Chaikin Lubensky, which is actually for classical statistical, classical condensed matter physics, almost many things. There is no point, no discussion on fracture, no Griffith theory, and fiber model should have been there. Nothing is there. Boris-Zubov model, I mean, Gutenberg-Richter is probably there or not there, I don't remember. Boris-Zubov is certainly not there. I just found, I mean, found out that even in archive, even in, Wikipedia, there is a Wikipedia site on this, what is this, OFC model, OFC model of earthquake. I mean, I've forgotten. Christiansen is the last one, and first two, I forgot. Maybe Takahiro can tell.
Christiansen.
Yeah. So there is actually a Wikipedia, I mean, in the encyclopedia, there is actually an article on, or an entry of OFC model. But there is nothing on Boris-Zubov model in Wikipedia. There is nothing on fiber bundle model. In Wikipedia, you cannot find this. I mean, we just have to take some initiative. Griffith's theory is also not there, but it is in fracture kind of thing somewhere it is mentioned. But I think, I mean, just Griffith's theory should be there, Griffith manipulation theory of physics. But anyway, and Gutenberg-Richter is of course there. But the thing is, even in popular encyclopedias, which anybody can, and this is freely available, nobody can find what are the recent things, particularly I think, I mean, for fiber bundle model. I tried once, I mean, they are actually now, they are very careful. They want to see how many people work in that and so on. So I think it is better that some, I mean, maybe Shoumo should try now, that he should open up, I mean, submit a proposal to open in Wikipedia a site on entry on fiber bundle model, and once it is there, after they agree, they will take a lot, and you have to connect with other places where somehow this model has been mentioned. Somehow, because they want to see that it is already in some form there in their encyclopedia. Now, these connections have to be made, researchers have to be connected so that they must be also in Wikipedia and so on. Otherwise, they will not. Now, I find this is an irony that we do not have that. More important is that none of the textbooks have textbooks of, I mean, I do not know any textbook, truly, but I think we should make some effort that maybe some of our friends or friends' friend, I mean, at most, I mean, it can go to this six co-author distance. We will certainly get Chaikin and Lubensky. I mean, what I'm saying is these 6 degrees of separation in the society. I mean, essentially that Erdos number kind of thing. That Paul Erdos is connected to all the mathematicians by 6 or 6. I mean, through co-authors, it is only 6 generation. So I'm sure there are, and we have to kind of tell them that it would be better to include fiber bundle model in their book, something like this, or and I'm sure some of us have closer friendship with them. Or of course, much more important is that some of us should write a kind of reasonable textbook which will be popular enough, including these, not excluding the other things, but including these. And in view of all these things, I had kind of sent a mail to a few of you saying that, I mean, maybe, well, this is not also original any idea. I mean, I found, okay, let me mention it explicitly, that Stanford University has opened up a online free encyclopedia on philosophy. Now that's nothing. I mean, of course, anybody can do it, and it's online free. But apparently, the dynamics is that philosophy is becoming, I mean, being viewed upon by younger students as a very old subject, is not coming to current topics, and they are not interested in philosophy. And that actually might kind of induce, and is actually inducing, closing down some of the departments in some universities, not necessarily in Stanford, but they have opened up this free thing, and then they have come to every, I mean, some latest developments in physics where some philosophical questions are there, then questions of computer science and people from psychology, they are writing, contributing on consciousness problem, not necessarily traditional economics, philosophers. Economics, most of the things, econophysics has been there and so on. I think, I mean, such an important, old, and extremely important and very potential subject is not appealing to young researchers. There are not enough people who are taking up on their own. And these writings are, some of these writings, I have not gone through any, all. Actually, I only a few, and I found that the Stanford Encyclopedia writing, even by physicists and so on, are very nice. I mean, it doesn't give any details, very small, I mean, very small introduction to the thing. There are some references to perhaps a very chosen small subset of references, and then some extra readings also, but with 2 or 3 figures at most, maybe without any equation sometimes. You have to introduce the subject and leave it to them, and then they will try to follow. Similarly, I think for kind of fracture, breakdown, earthquake, there should be a kind of online, freely available site, maybe the Fracmeet site, or if somebody else agrees to host the site, there should be a site where people can be invited to write very, and very active group of people are for a very popular level introduction, and then taking towards the research level, and then give the one or two small or a few references, so that they can on their own study. And if mostly if that is also online free, the references are also online free, so then it will be extremely useful. There are some papers, not always everywhere, and this kind of site should be there for younger people to judge on their own and come to the researcher. Not young means, it should start from school leaving students, but I'm not only leaving at there. Even the postdocs and others, they should take up the things after they have seen on their own what simple models can do, and how these intriguing the models are, the results, importance of the results are, and so on. So I just have a this kind of loud thinking that if something could be discussed here also. So I just leave at this point. Shomo, you can take over from here.
Yeah, thank you so much for your comments. And yes, of course, this is really important to have that kind of.
Sorry, who is talking now?
No, I am.
Oh, okay.
So yeah, if anybody has anything to add, so I asked them. This is just an open discussion and an informal one. So if anybody has anything to add, please unmute yourself. Yeah, Puruta, if you have something to say.
No, not as such. We have all felt that what Professor Chakraborty has said is correct. Fracmeet originated from this kind of idea that even in soft condensed matter course, not only course, there are so many meetings, discussions, and so on, conferences take place, but fracture is never a part of that. So that was the origin of Fracmeet, which we have been. But even now, I noticed that it has it attracts only a few people, not the quite big, larger, part of condensed matter physicists. So I definitely agree with what Professor Chakraborty is saying, but yeah, one has to say that. So I would say request that if anyone else has any kind of views on these, or on this meeting, or on anything else, one can share.
Yeah, if not, then let me thank again all the speakers of the conference, and I also want to thank, of course, my co-organizers. Miko is here. Yeah, Miko, and that's all right. So yeah, I thank all my co-organizers. Purushottam Ray is here, Ranjita is also here, and also the technical team here in SRM AP, who has helped us quite a lot in, for example, recording this and live streaming this on YouTube, where the all the talks and actually the whole proceedings is freely available in YouTube, so that other people, especially in different time zones, who couldn't attend all the talks because of their prior commitments, or also because of difference in time, they can listen to those whenever they want. Yes, Miko is saying that he pointed out about the YouTube part. Yes, thank you so much. Yes, so yes, our technical team has been very helpful to make it successful. And also, I want to thank all the participants who have participated here. Of course, we couldn't have a physical meeting this year, unfortunately. That, of course, is a great loss, but this is the best we can do at this stage. Hopefully, in the coming years, we will have a better situation and we can host conferences in the way it should be done. Yeah, with that, thank you all. Thank you all for joining, and hope to see you.
Thank you, Shomo, and thank you, everybody. Thank you, all the speakers, and thank all the attendees. Thank you.
Thank you so much. So I'm going to end this here. Thank you.
Thank you very much. It was a very nice conference.
Thank you. Thank you.
Thank you.
Thanks. Bye-bye.
Bye.
Bye.